Yes, people are coming and coming, but we cannot wait. It's a very tight program, and I guess you all know me. I'm still Dmitry. I'm still working with Taltech, with the Department of Electrical Power Engineering and Mechatronics, and I'm still a leader of this nice event, Estonian DC Innovation Workshop. Today we are meeting for the 6th time already. We are creating a history. Andrei, thank you for interrupting. Now the picture is back. And the good thing is just this was the initiative of Taltech. Taltech is the only technical university in Estonia, and the electrical engineering is given only in Taltech. And so we are proud to be the representatives of electrical engineering worldwide, of Estonian electrical engineering. And for the opening remarks, I would like to invite our rector for entrepreneurship. Eric, I always forget the full title of your position.
Thank you, Dan. Good morning to everyone. I am just finalizing the new development of strategy of the university. So after my speech, I'm running back to make the last changes. But I must say that what is happening here today is one of the highlights of our university, and it's extremely important for us. Because and especially because we see that the future is in interdisciplinarity and connections between different fields. This is something we are feeling stronger and stronger. So it is really nice that this event has gaining more and more momentum, and all this topic also. And I just wanted to tell my own story. Recently, my wife called and told that her friend from university times is in big trouble. The car doesn't start, and can you come and help? Of course, I understood that what is my potential. Of course, when I was doing my military service 40 years ago, I was responsible for loading the batteries of the cars, but this is the only thing I can do. But anyway, you are from the university, and so I went to the parking lot, and there was this little bit older type of Toyota Corolla, which is actually a perpetuum mobile, as you know, but the engine didn't start. And there was a family, there was 3 generations, there was a dog barking. So I did the only thing what I can do. I took the wire off the battery and put it back, and the car started. And so everybody was looking with me, who's a great admirer, and how did you do it? And then I could say that we have this wonderful DC group in our university that has a but the message of this story is that if you really believe in yourself, then you can do very great things from the university, and this is and this is exactly what we are doing here. So I wish you a excellent conference, and let's do great things, because this is something the universities are for. Thank you.
And thanks, Eric, for setting up the mood. Yeah, it was a lot of jokes. It's engineering humor, right? I will try to keep the pace. I will briefly introduce you what this seminar is about. I expect many of you knows what is DC, right? Do you know what is DC? Huh? No one knows. But this is a good place to understand and to learn what DC is, basically. And the idea of this event is to raise the awareness about new energy saving technologies. Basically, DC is all about energy saving, energy performance, the best we can use. I would like to mention sponsors, as usual. Once we start, we need to declare very good money for this event. And for this event, it's I3DC is our Taltech's initiative to promote DC. It was my venture. We got some money from Center of Excellence in Energy Efficiency, that's the Estonian body. dealing with some research topics in the field of energy performance of buildings. Estonian Research Council, ETAC, and some money we also received for this nice coffee from the European Union. But, Andrei, my slides doesn't move. I'm trying. This pointer works, but slides can. Oh, I have to understand where is the receiver. No, it cannot see the receiver, Andrei. Okay, that's a good idea. But you have to stay there as well, right? Still no way. Yeah, that's a technical problem, not connected to DC. No? Let me check. Oh, magic. You need to power on the remote control. I told you, just to relax you. It will be a lot of jokes, by the way. But what is DC? And now it's very trendos. I am not using AI at all, but it's very nice. Usually, every first slide of this official speech starts from the. I was asking my friend AI, what is DC? And yesterday I was asking my friend AI, what is DC? And they are the answers. DC is the District of Columbia. It's true, right? The second option is it's a Detective Comics, the origin of DC Comics. I don't know what is it. Any of you knows? But it's very popular. The second popular. Me not. Data center. Okay, no life without data centers today, right? It's a DC, by the way. Abbreviation is still DC. It's a data compression, something in computer science and digital storage. Delivery confirmation in shipping. Default configuration in equipment software. Doctor of chiropractics. It's also DC. Decompression chamber. Any of you are the divers, or you maybe, right? Well, you know what is decompression chamber, but it's DC, right? And my son yesterday told me, look, it's a DC, it's a don't care. In TikTok, they use it a lot. It's a don't care. But the point to be here to explain you that DC is basically it's a direct current, right? And all of you know, I guess, you wasn't reacting on my message, but actually all of you, right? From the school course of, I don't know, physics, this is a direct current. You remember these two options, right? The option A is here. What you are using today is alternating current. It's everywhere. And the direct current is just the straight line, It's a battery supply where you can see the direct currents in the battery, right? And these two gentlemen, one was for AC, the second one was for DC, AC1. If you do not remember the history, I would recommend you to, Andrei, it's again, to see, right? And it will explain you everything except for the physics of the currents, right? But anyways, very nice and educating movie. It's very nice. I mean, I really recommend you to take a look, to check it. So what of currents? It's a return of DC. Very fastly show you that. Today, a lot of talks about data centers. And I was asking my friend AI to answer me what is DC, burning a lot of energy, but all this energy is delivered by DC. All data centers run on DC. Airspace, and I put this nice picture of the Boeing Dreamliner 787, right? The biggest part of this aircraft non-bleeding system is DC system. Telecom, DC forever. Renewable energy, all PV power, battery storage, everything you can imagine, it's just purely DC. Electromobility, so it's Marius for you, your favorite car, Tesla, I think, right? What is the model of it, And this guy was enjoying testing it, acceleration 2 seconds to 100, right? Lighting, LEDs, all DC. Home appliances, everywhere you can see inverter sign DC, so powered by DC. And consumer electronics. And many more, HVAC, power system, industrial system, and so on. Estonia and DC, by the way, I'm just warming up, since it's something we talk about DC, not in Germany, not in France or Netherlands, right? But in Estonia. Estonia has a DC story. And the DC journey in Estonia started in 1959 in Estel company, and they started production of mercury rectifiers. By the way, Harry, I guess your business was also starting from the rectifiers. All DC business starts from rectifiers. Estonia started writing a history in 1959. And in 2006, Estonia was launching Estlink 1. It's the first 350 megawatt HVDC line between Estonia and Finland. And now you see the Estlink 1 is here, but the second one is Estlink 2, and the total power peaking 1 gigawatt, sorry, yes, thank you. And another thing quite remarkable, it's Estonia was the first, has the first nationwide EV charging network. So built up by ABB in 2013. Actually, Estlink 2 was operational in 2014. So basically, Estonia was creating records in the DC book. Today, we're also talking what is next. Basically, there are a lot of success stories before, and they're new coming. And also our industry and our, let's say, academia work hard to bring some new records to the DC book of Estonia. And today, basically, we have a very nice event, very friendly, quite relaxing atmosphere. Don't be overstressed, all the presenters as well. So in cooperation with two biggest alliances driving DC in the world, it's Current OS, and Yannick is here, the president. Can you tell us a couple of words, very shortly, just to demonstrate you the president of Current OS, the biggest.
Hello, everyone. Thank you for being here. And a lot of time people are asking me, well, DC, okay, but it worked well. This is all about NEC system and it worked well. Why change? Well, I just remind you that in April this year, there was a blackout in Spain. And the question is, well, my question is not why did the blackout happen? The question is why it was a sunny day and people had no electricity inside their house, even if they had PV on the roof. That's the point. DC could solve this.
Thank you. Very short. And Odyssey does industrial. I still would like to stress industrial, right? And not German, but worldwide, right? Hartwig is the president of Odyssey. Yes. No.
Yeah, thank you, Dmitry. I'll keep this short because you'll have to listen to me twice this morning at the end of the first session and also, I believe, in the second session. The Open Direct Current Alliance is an international organization. The roots are industrial. We are about direct current, I feel, among friends here. So enjoy the event. Thank you.
Thank you. Yes. And I brought here a bunch of my friends and also our partners. By the way, this expert, Harry Stockman, is here. So it's the most known person in the world, I would say, for the last 20 years about DC. So he was pushing all things in Brussels, everywhere, right? I mean, we can reference you all the time. So the Eaton company, Hartwig will represent Eaton as well. DC Systems, DC Apparatus, and Ambibox, basically, these companies already created some business cases for the DC, and we have to learn from them. And actually, they're the bunch of Estonian companies. Okay, Elering is understandable. It's everything about Estlink. So we will listen to a story of Estlink. But Skeleton, it's a very well-known company dealing with the supercaps. It's a DC technology. And the Berchmann, so the company dealing with the EV chargers. And also Taltech. Taltech will show you a bunch of new use cases we will be developing for the next 3 years. So it will be quite nice and quite inspiring event. And driven by the i3DC initiative, it's our Estonian initiative to push DC and to mostly to promote and to raise the awareness. What we do before we introduce DC, it's a brand new technology. We need to raise the awareness. And basically, this is what we do today. And wrapping up my speech, i3DC I also realized, thanks to my son and yesterday, i3DC, I don't care. IDC is I don't care, but actually it doesn't equal to I don't care. i3DC, it's inform, inspire, and innovate. So everything you must know about DC. So enjoy your day. And we are starting with the main program. And I guess, Mario, you are the first one, right? Yeah.
Yeah, I'll introduce myself. I don't have any slides, so you can give that to Karin. I decided I'm not going to make any slides because Karin already probably made very beautiful slides about all the energy policy coming up in the next 10 years. So I'll just talk. That's what politicians do, right? So just as a quick intro, I'm Mario. I'm a member of the parliament, member of the economic committee. So usually everything that is related to energy, electricity, etc., always tends to fall on my lap. So that's probably why Dmitry invited me here. But I'm also somewhat background-wise a researcher. I have a PhD in experimental particle physics. So I was part of the Higgs discovery, but I decided I've done enough for the world in particle physics. Now I want to do something elsewhere as well. And I do have some direct connections with DC as well, in the sense that as a hobby, I do my own energy systems as well. So this summer I built, because photovoltaic isn't really profitable anymore because we have too much PV. So usually if there is enough sun, the price isn't zero or negative. So I built my own battery system, 185 kilowatt hours, high voltage system. Also managed to get direct connection with DC in the sense that we managed to accidentally short 300 voltage system. But it was not a big explosion. So all is good. In any case, I do have experience with DC. I was a part-time professor here in the university as well. But overall, electricity system-wise, because Dmitry gave my talk the name of the energy policy of Estonia, I would have to say that Estonia used to have our energy policy has been changing over time based on essentially externalities. So up until recently, the highest priority, of course, was to get away from our old energy system. And the old energy system was essentially from the occupation time, meaning that we were extremely reliant on oil shale, which is a fossil fuel. It's somewhat even worse than coal, at least emissions-wise. And we were tied to the Russian electricity grid. So there were pros and cons to it. The pro was that it was really cheap for balancing. Didn't really have to worry that much about balancing because the Russian grid was so big, they'd balance it out. Of course, there was some partnership involved as well, and being partnerships with Russia is not something you really want these days. So for quite a while, there was a project to disconnect the Estonian grid from the Russian grid and connect it to the European one. So this happened this spring. Went relatively smoothly. We did operate as an island for a short while, and I think it was just recently, like a week or two ago, that we were officially taken into the European bed. So now we are in the European grid. Of course, de facto we were there already in February when we connected back, but officially it was passed only recently. So that was a big transition. That, of course, means that now we have to take care of all the balancing. And because we are a region which is in deficit, then, as you know, with AC, what Dmitry was trying to point out is that it's kind of annoying. You have to keep it in balance, unlike DC. We do have to maintain our own frequency. So this has created interesting things in the last half a year or so. So there's a lot of change and shift in the marketplace. Lots of batteries coming online, just to make sure that the system is stable. Future-wise, recently, we used to have a target. By law, we still have a target that we should have 100% of our net usage also produced through renewables throughout the year. Of course, it's not second to second, but it was considered as a net. So if we use about 8 to 9 terawatt hours per year, then we should produce also 8 to 9 terawatt hours per year from renewables. That was a nice thing to have as a goal. We were actually progressing quite well on this front. We saturated on photovoltaic. We were going with wind, but as usual, There is a NIMBY and the banana, which always come into play. So the planning effects have been so and so. I see that guys are testing out all the things that electricity can do, for example, light. But in any case, then you could say that the proverbial thing hit the fan in 2022. And you had to kind of also reprioritize. So clean energy, of course, is still a must. It's still the cheapest form of electricity, but you also need security. I mean, disconnecting from the Russian grid was also an element of security, because before we had everything in place, there was a big, you could call it rubilnik from the Russian side, that they could have been pulling, and we would have been emulating Portugal. These days, or essentially already late last year, the situation was that had they done it even before we officially disconnected, we would have survived. But it took a bit of doing. In 22, they could have killed us electricity-wise if they wanted to. In 24, not anymore. So we had to kind of refocus, shift our focus. So we had to move towards energy security. And this means that this is also reflected, so this is kind of a teaser for Karin's talk. It also reflects in our energy policy changes in the next decade. So we still maintain that we want to have 100% clean energy, but not for 2030. That's a bit of a tough one to push it in 5 years. Also, it would kind of shock the system, unintended. But we will maintain it. We'll push the goal forward to around 35, 40. And we don't call it renewable, we call it clean. Because essentially, I think this is the shift that most of the world is actually doing, is that understanding that you probably want to have also stable power sources, not only variable power sources in your electricity mix. So we're also looking towards nuclear as an option to provide base load, which helps both in stabilization as well as in general, we are in high deficit. So these are the kinds of changes we are doing in the energy policy. And of course, considering that the whole region of Baltics is in severe lack of energy, what you guys are going to talk about and are doing is also important, because in electricity systems, there are always two components. There's production and there is consumption. And you can try to fix the system from both sides. One is, of course, you can try to increase production, change the mix, change the technologies there, but you can also do it from the consumption side. You can try to make the consumption more efficient. You can try to make the consumption more intelligent. I think these days, what you mentioned, the easy answer is replace your inverter. So you have a hybrid one with a battery, then you can keep your grid locally. If the wider area falls off, that's what I've done at my home. Just recently, I was seeing a Facebook chat in my neighborhood where everybody was talking about the flickering lights and what's going on. And I said, I don't know. Then I checked the inverter and saw that the grid had been disconnected 5 times. Okay, didn't really care. So, I mean, you can do these kinds of things. You can do better management. I mean, these times, usually what is the biggest consumer at the home? It's not your TV. It's going to be your HVAC system or something similar, heating system. If they're intelligent, if your house has enough inertia, especially with floor heating, for example, you can vary your consumption in the 24 hours pretty well. You can adjust it to when you have production and when you don't have production. So intelligent systems, efficient systems work. And I guess what I've also talked with Dmitry and what I kind of knew also in advance is that DC is the more efficient method. I mean, we're doing a lot of AC-DC conversions. And by that, I don't mean people going away from Metallica to AC-DC, but just the power conversions. One of the reasons why I built my battery high voltage is a simple effect. I mean, the solar panels come in at around 500 volts. The DC at high voltage is also around 500-600 volts. I lose less. So I only lose about 10%, not 20%, which would be with low voltage systems. So again, all of those things do pile up. If we have, I would guess, at least 10-20% losses in the household, probably more, depending on the systems. If we could eliminate that, we could eliminate 10-20% of consumption. If we lose 10-20% consumption, it means we reduce also the deficit. So there are a lot of things that can be done. In this sense, I think it's a very good thing that Dmitry is doing here, and I always keep an eye on it. I'm also keeping an eye on what's going on in general in the country, but knowing also that these kinds of systems are not ultra fast changing, and nobody's going to rebuild their home electricity wiring what's already been built, at least not easily. This means that, of course, there's going to be some nice innovation that you guys have to do, so it would be plug and play, essentially. So if something that can be done from the state or electrical distribution side, of course, there is that. Doing power lines using superconductors and DC would be fun. Of course, somebody would first have to invent room temperature superconductors, but that's a small thing, right? So overall, I'm already starting to yammer. So I think it's better to hand it over to people who will explain where we are going, now that I've given you maybe the general view of what we've rethought, what is the priority and which way we are going, then to somebody who is actively working on this from the ministry side, and Karin can explain to you all of that. But if you have any questions, I guess I still have a few minutes to take a question or two. So right now, the grid has originally been built with the intent that all of the power is produced in one location, essentially. The oil shale power sources were all close to Narva or in Ida-Virumaa. So the grid is built as a tree falling from that region. Within the push for renewables, already the grid has been somewhat reworked to also allow power supply from the other direction, because people are installing the PVs everywhere, right? This has also been a bit of a limitation. So if you want to add panels to your roof and you ask for an option for 10 kilowatts and they tell you it's going to cost you 2.3 million, then you understand that they probably need to change the high power line somewhere. So it's a slow moving effort. I know that the distribution grid is also considering adding into the transformers that they have regionally to add also some extra capabilities, for example, either batteries or to use the batteries inside homes to stabilize also the grid locally. Of course, 99.9% of the inverters that people use at home don't have grid forming. So this means that this will not help you during blackout, but it can help during the stabilization while the grid is still on. So if it goes out like it did in Portugal, we still have to restart it from grid forming locations. We do have a number of them, not only one. We used to have one, now it's a bit more. And I think when we have more big battery banks coming online in various locations, which are dedicated battery banks, not home battery banks. Yes, so, but I think also what is happening is a lot more people are moving to hybrid inverters and island capable inverters. So you can keep your household operational even if you lose the grid. So this will help somewhat, but this is still a huge minority. I think we have batteries in about 1,200 households, which is not small. It's increased by a factor of 8 megawatts wise from last year. So it's quite an exponential growth, but it's still early days.
And one second question. Do you also consider, because of the NAVO budgets, that you can spend 1.5% on infrastructure? Is that used for grid robustness investments or?
Well, that's something you can ask from the Ellering guy later in the session. But I think we'll need most of the 5% for shells because, I mean, hybrid attacks are already ongoing, sure, but we also have the actual physical threat option. So we need the 155 and other shells initially. But I think, yes, I don't see that we would be dropping from the 5+% GDP defense spending anytime soon. And of course, once we get the initial capabilities, all the armored trucks, all the HIMARS and everything else already delivered, we have a lot of that already happening this year. I think it will start to look also in other, I mean, we do have also regional security, internal security, all of those are in it. So I would expect also the resilience of the electrical grid. We do have something called life important services. So telecommunications, electricity, medical care, food, those are considered operators of life important services. So by law, they have to have different standards. And that also includes that electricity availability and generation capabilities have to be improved by those operators. So if you are operating a substantially large power plant, you have to take care of things to also be able to operate during crisis situations.
Thank you.
Thank you. And of course, applause. And thank you, Mario, for your time. And it's a special gift for you to drink your nice DCT. Yeah, it's a small gift, but memorable. Thanks again.
Sadly, I do have a security briefing in half an hour, so I can't remain to listen to the talks, but I'll get the summary from Dimitri.
Yes, absolutely. And we'll also publish with Trialog. I guess we'll publish a very nice, how to say, column, or even longer. I guess it could be a, how to say, how you call it, paper or a brief or something. Overview. Excellent. So thank you. And keep in touch. Yes. And yeah, we are moving with our program to the next speaker. But before I introduce the next speaker, I would like to show you a very good example, by the way. If you want to learn, you have to ask. It was a good example by professionals, but PhD students. This event is also for you to learn. Please come closer and ask more. So the second speaker, but actually it was already an announcement by Mario, right? So Karin will talk us about vision of power system and energy in Estonia.
I think I have
everything.
already microphone.
Excellent. Thank you.
Okay, thank you. So yes, I'm Karin-Maria Lehtmets from Estonian Ministry of Climate, from Energy Department, and head of Electricity Market Unit. And we are dealing not only with markets, with electricity and gas markets, but also with grids and security supply issues there. And Mario knows me quite well. Indeed, I have slides with a lot of numbers, so I hope it's not too boring. But I want to give you the overview what we are thinking in the ministry, in what way we want to move with the energy policy and visions. First of all, a little bit where Estonia ranks in the global energy economy compared to other countries. And I think the most important ranking, or what we are looking in the ministry mostly, is the World Energy Council Trilemma Index. And at the moment we are on the 7th position compared to 126 countries. And WEC Trilemma compares is looking like in three main things. First is sustainability of energy system. Second is security of supply of energy system, and then affordability of energy. And yes, Estonia is sharing the 7th position with Germany. and Denmark, Sweden, Finland are the first 3. But there are also other rankings, for example, Sustainable Development Ranking, where we are on the 17th position, and Yale Environmental Performance Index, where we are at 1st position. That was a surprise for me as well. And at the moment, we are working very hard in the ministry with our energy plan for 2035. This is going to the government in coming weeks, and then to the parliament, and will be enforced in few months. And we have prepared it for several years already, a lot of research done. But the overall goal is that Estonian energy economy ensures energy security, enhances the country's competitiveness, and directs the transition to economy with a clean energy. So very similar with the World Energy Council trilemma approach. And now a little bit about the numbers, where we are at the moment and where we want to move. So at the moment, we have renewable electricity compared to consumption, 32%. By 2035, we see that 100% of renewable energy is probably not reachable. We are wanting that, but at the same time, we see that if we want to move on market-based, not too many subsidies, then probably we will reach 70 to 80% by 2035. Maybe 100% by 2040. And by 2050, the goal is to have a total climate neutrality, not only in electricity, but the whole energy. At the moment, we have wind capacity almost 700 megawatts. And wind is the main production unit what we want to develop regarding looking in the future by 2035. And we see that we need probably 4,000 megawatts of wind. This mainly includes onshore wind, but also we hope to have by that time one offshore wind park, 1,000 megawatt. Solar we have already quite a lot, 1,200 megawatts. It is already more than our peak demand during summer times. So it is a lot. And that is the reason why we see that probably the increase in solar is not so high as it wind, but still some increase we expect. Storage, by the end of this year, we have 133 megawatts. We started this year with 6 megawatts. But as Mario already mentioned, at the beginning of this year, in February, we disconnected ourselves from Russian grid and synchronized with continental Europe grid. And that also, due to that, we also had to create new balancing reserve markets. And storage is a very good resource participating there. And due to the reason that we expect a lot of wind by 2035, we also expect a lot of storage that will help to balance that, will help with the balancing reserves and also in the day-ahead market with the price peaks. Dispatchable capacity need. This is a quite important topic. I have a dedicated slides coming regarding that topic. But at At the moment, we see the need is a little bit over 1,000 megawatts to ensure security of supply and also island operation capability. We have more than 1,700 megawatts, but this is mostly on old oil shale. And we are phasing out from oil shale. So this is a challenge, how to ensure enough dispatchable capacities also by 2035. And we see that the need is rising rapidly. This is due to rise of consumption, rise of renewable energy in the system, and it will be probably more than 2,000 megawatts by 2035. At the moment, the system is a net importer. We are mainly importing from Finland because the prices are lower there. But our goal is to become again net exporter. And we have 2 connections DC current with Finland, Estlink 1 and Estlink 2, and 3 connections with Latvia. And by 2035, we expect to have additional connection with Latvia. And we also plan a 3rd Estlink, but probably this will be ready by 2038. And sorry, I have a mistake here. It is not 1,000 megawatts, but 700 megawatts. I did the slide 2 a.m. today. So the main goals and challenges for our system is how to ensure enough dispatchable capacities in the situation where the oil shale units are closing because they are not competitive against the market anymore. At the moment, we are keeping them up with dedicated security measure tools, I would say. But we are also working out new market-wide capacity mechanism that should bring new production units by 2035 the latest. And probably these will be mainly on gas because this is the fastest with the fastest reaction and helps in the balancing market. Also, it is quite, the goal is to increase the renewable electricity part, the wind mainly, but without additional subsidies. So this is definitely a challenge. And we have a very high NIMBY effect going on. So we don't, there are a lot of wind parks on the planning phase, but they are not ready in several years. So there is a lot of work to do with local municipalities and local people to break this NIMBY effect and show that wind parks actually bring lower prices and also better system security, I would say. Also, the goal is to increase the flexibility in the system. As showed, we hope a lot of storage, battery storage, but also a demand response. Demand response is at the moment already on the balancing market involved, but we want to open day-ahead markets for independent aggregators and to have more flexibility also there. We have challenges also in the grid side because first, distribution grids need a lot of investments, and we want to reduce the average outage time per year there. In last 5 years, the average has been over 200 minutes per consumer, but we want to reach lower than 120 minutes. Probably it needs about 1 billion investments. with these 10 years. Also, the rise of hybrids in the grid, as we have had two very serious incidents in last few years in the Baltic Sea, as first the Baltic Connector case, the gas pipeline with Finland, where there was an anchor incident and pipeline was out of work more than 6 months. And then just before the synchronization, 1 month before the synchronization event, the S-Link 2 cable was taken out again with anchor. So we already have had, I would even say that these are hybrid attacks. So we are putting effort to secure our grid against the hybrid threats. This means increasing underwater resilience systems, monitoring systems, also increasing equipment stocks, and so on. One very important goal that we have in this our new document, I would say this energy strategy by 2035 in the ministry, is that the end consumer price of electricity for all consumer groups in Estonia must be below the average final price of other neighboring regions. And this means that, yes, we need investments in the grid, we need investments in the dispatchable capacities, also to renewable electricity, but we always have to look that the overall final price wouldn't go too high. And at the moment, if we compare us with neighboring region countries, then regarding households, we see that the average price is lower than averagely, so quite okay. But the problem and improvements are needed regarding larger consumers. So this is where we have to put our effort. And now a little bit more about this dispatchable capacity issues. I have here shown steps regarding the grid and up regarding the dispatchable capacities. So what we have done and what we plan to have enough dispatchable capacity by 2035. First, this year, Elering had a procurement against this regarding this balancing market setup, and they procured 150 to 5,000 megawatts of capacity, and the procurement brought us 236 megawatts. So this is there are a little bit of storage, but mainly gas units, and these will be probably ready by 2029. It is not usual that we can make these kind of procurements. This was like I lost the word in English, erand, exception given us from the directive, from the European Union directive. Because usually these kinds of procurements need state aid permission, which is quite hard to get. But fortunately, we got this exception, we got this procurement, we got additional 200 megawatts to the system. Then we created two security supply measures. First is island operation capability. This we will start from 2026. And Elering has calculated that we need 1,036 megawatts of capacity, to be ready even in the case when we lose the Latvian lines, when we are in the island operation. We have to decrease the S-links amount then to 200 megawatts, because this is the largest amount that our system can handle at that time. So this is the amount that we procure yearly. And oil shale units are offering that, but yearly measure doesn't bring new capacities. So this is helping us to keep the old units in the system to ensure security of supply. But for a longer run, it doesn't help us, because by 2035, the oil shale units will be shut down anyway. And the second security of supply measure is strategic reserve. This is a measure that needs state aid permission. We got the state aid permission in, was it end of September or beginning of October this year? And the mechanism can be ready by 2027. And we will not use these two mechanisms together. We will see which would be cheaper, but this is like a plan B. Probably the island operation capability is better for the society, but strategic reserve is like a plan B. Also yearly auctions helping to keep up the old units, but not bringing new. What we are planning regarding new units. We see that we need market-wide capacity mechanism. This is at the moment the only measure in the EU law that we can use. But to work out this design is takes quite much time. So next year we are making analysis regarding the design. Then we start with the state aid process, and the timeline shows that the earliest we could get the procurement out 2029, which means that the new units can enter to the market probably 2034. So this goes well at the moment, because 35 we lose the old shale, so the timelines match. And I would also like to mention nuclear, because at the moment we are working with the nuclear law and to have the nuclear regulator ready by 2027. This will open the door to this possibility. But of course, if the new SMRs are coming or not, this depends on investors. We have one investor who seems to be really interested, and we hope that it is possible to have a small modular reactor ready by 2035 or 2040, but let's see. But from ministry side, we are very willing to open that door, because we see that the small modular reactors I would say they fit in our system quite well. Okay, I have also the roadmap regarding storage and demand response. I won't go very detailed here, but it just shows that, yeah, by the end of 24, we had only 6 megawatts of storage. The opening of frequency reserve markets helped to raise the amount quite a lot, and we are expecting the storage level by 2030 to increase 1,200 to 1,500 megawatts, and by 2035 over 1,500 megawatts. And there is also one project regarding long-term storage of 500 megawatts with pump hydro storage. There are discussions ongoing from the investor side, but it could be also a possibility by 2033 already. And Very briefly about the renewable electricity regarding the wind. I mentioned that we do not see new subsidies for the wind, but still there will be in the next year one subsidy tender regarding 1 terawatt hour with the possibility to increase it up to 2. But this at the moment we see that this will be last. And we expect to have onshore wind almost 2,000 megawatts by 2029. Offshore wind could come 2033, 2035 in the amount of 1,000 megawatts, probably with one park. And overall, the renewable capacity amount could be almost 5,700 megawatts by 2035. So a lot of numbers, and I hope it wasn't too boring. Thank you.
Thank you, Karin. Yes, we're a little bit out of time, but anyway, still I take a risk, sorry, to invite one question very fast. I noticed there are a lot of pictures were taken during your speech, right? So people are really interested, but it's a very nice chance to ask. Yeah, please come here. That's why I told you it's much better to sit here. It will be easier to interact with you. So yeah.
Thank you for presentation. A lot of great information and prospects. I'm a PhD student from Finland. So my question for you is, do you see a significant role in the frequency reserve market coming from the residential consumers? So considering we have, I don't remember the figures, but we have a lot of renewables and battery storages coming from the residential consumers. So do you see a significant role of that in the demand response to the market, to the Estonian power market?
Yes, thank you for your question. We have opened the market for independent aggregators already. So we hope that in their portfolio also residential consumers can participate. At the moment, the amounts are not big, but when opening also the day-ahead market, what we are working at the moment, this probably creates a bigger business case for aggregators, and we hope that their portfolios will increase and they will involve also residential consumers. I know there is one company, Voltalis, who is a French company, who is their business model is especially regarding residential consumers, and they have said to me that if you open the day-ahead market, then I will come to Estonia. So let's hope.
Let's see. Thank you.
Thank you. An applause. Karin, it's for you.
Thank you.
So, yeah.
Thank you. Ma pean varsti ära liikuma.
So you can communicate now. So, thanks a lot. And we are moving to the next speech. Next speech is from Hartwig. I think Hartwig is here. Andrei. Andrei is preparing for you something. Yes. So far, it's a very nice chance to move those who are sitting on the back. Here, please. We will interact. Please. Don't be afraid. It's very safe here. And it will be a privilege to sit with these famous people. Come here. The second row is for you. No stress.
Yeah.
Any of you. We have. It's not a conference. It's not a PhD defense.
Yeah. All right. And
It's my PhD defense today. It's not yours. Relax. The pointer is here, Andrei. Pointer is here.
yes. All right. Yes. Yeah. All right.
Now it will be a very
Oh.
interesting talk, by the way.
Yes.
Starting from Brussels, right? CET plan,
Yes.
and this gentleman is a VIP person
Oh,
in the strategical planning on DC and energy performance
Yeah.
of Europe.
You're exaggerating
Exactly.
greatly, Dmitry. But thank you very much. I got wired. Sorry for the for the delay. I'm the chair of the Open Direct Current Alliance, but I'm talking here as the co-chair of the European Union Strategic Energy Technology, DC Technologies, along with, and Harry, please stand. Harry is my co-chair in that capacity. And I also have to give my kudos to you, Harry. You are the one who introduced me to power electronics. For my educational background, I'm actually electromechanical engineer doing protection devices electromechanically, but I've since learned that power electronics is way superior. I hope the slides that I took a few minutes or a little bit more to prepare will show up in a minute. I've seen them there already. I will be talking a little bit about why we're doing this, the motivation, what is the, I may call it the strategy within the European Union towards sustainability, and also on which documents have been prepared and what we have been doing within that DC Technologies group. And here we go. I see myself there. It will work. All right. Okay. Thank you very much, Andrei. So this is kind of the content, and we'll start with the motivation. So why do we do this? And I trust you all have heard of the IPCC, the International Panel on Climate Change. That is a panel of scientists, very, very many, tasked by basically all the governments of the world to evaluate scientific knowledge about living conditions on this planet. They don't conduct their own research, but they give summaries for decision makers every few years. And in the last report 2 years ago, they had 10 key solutions prepared. And already number 2 on the list of key solutions is energy efficiency and clean energy. And this is where direct current specifically also plays an important role. In a way, you could say, okay, the science says it's unanimously agreed. There are some fringe people who say it's a hoax or whatnot, but that is actually the hoax. If we would listen to the science, we wouldn't need the second part, the international law part. 10 years ago this month in Paris, the Paris Agreement was signed and agreed upon by all the signatories, committing to not exceed global warming by 1.5 degrees centigrade. Of course, that is a global average. The land mass here where we are heats much faster. So that is already a challenging position. This summer, the International Court of Justice has ruled this is not just a lofty goal, a piece of paper that people have signed. It is binding international law. Just as don't invade another country, don't kill someone, you have to impose measures to fulfill these targets. Now, the court doesn't have a police or an army to arrest you, but decision makers everywhere, be aware, this is your obligation. And if science and law is not enough, maybe immediate need. This is a map of the Netherlands, and it shows in color code where can you extend or renew or build up a new electricity connection. And everything that is red, thank you for asking, come back later. It's not possible. So we need different solutions to get, even if we don't like the science or the law, if we like to have coffee or light or industrial production, we need to do something. And what has the European Union done in that part? This term set plan stands for Strategic Energy Technologies, and that was adopted by the European Commission as part of the Green Deal to ensure technology-wise that we can fulfill our climate commitments. And direct current is one of those technologies. There is a website there, the set plan information system, EU, just like many of us like their acronyms. That's what that stands for. And direct current is one of the about dozen technologies. And along with others, efficiency, and in industry and in commercial applications. Mario Draghi, the former chair of the European Central Bank, I think last year or a year and a half ago, was tasked by the European Commission to have a look at the European Union and the key challenges. And he wrote a report, and it covers a lot of things that you all read or hear about in the news. There's also a part on messages for the electricity system. And in a nutshell, I'll go a bit faster. The existing AC distribution grid is not up for the task to electrify our energy system. Remember, electricity, I believe we're all more or less related to electricity in our educational background. Does not cover everything in our energy supply now, but we need to shift to clean energy, and that will be electrification. Originally, DC in the European Union was only high voltage. Long distance transmission, point to point, high voltage DC. And last year, it was broadened to include low voltage direct current and renamed to DC technologies. In that group, we have prepared a few documents. I'll show a couple. One is before I start that, like we started, I think 3 years ago. I see a few people who were involved in that process, workshops conducted by the European Commission. What is that thing with low voltage DC? Can it help us? It led to adopting low voltage DC in the annual set plan conferences last year. And finally, a workshop was conducted at the beginning of the year where it was officially announced. And for low voltage DC specifically, we created a implementation plan with 4 key topics the European Union shall address their efforts to. And number 1 is make it a reality, applications, put it out. Research is important, and that will be covered, but the most convincing thing is when people see it does work in my neighborhood, in places that I can read about and see. The second thing is that is also where research comes in. Further improve power electronics. It has improved in leaps and bounds. 20 years ago, this would not have been possible. It's the way it is now. The third thing is the people who install and plan electrical installations, they need to have the tools available to do it the efficient way. Currently, it is almost always based on alternating current. And finally, education and training, both in universities, in vocational schools, make people aware that this is not just a thing for the toys of your children or your flashlight. It is for general electricity needs. This is a worthwhile white paper, 2 pages only, where we talk about the resilience aspects of low voltage DC. It's inherently resilient, and I believe you'll hear more about it. Harry, you asked already about that. In the simplest form, there's no external communication needed, and so that way it cannot be compromised. That way, cyber secure by design. It is addressing the topic I showed with that map, and that is by far not an issue only in the Netherlands. It comes it is the same in other countries as well. By supplying power locally and storing power locally to cover peak power. And of course, it's just the efficient way to do things. What have we done within the low voltage group, and also like some activities within the European Union? One is that workshop that I briefly mentioned already in January in Brussels, where people from the Commission were there talking about both high voltage DC and low voltage DC. I had the honor to be speaking there on behalf of low voltage DC. And that workshop had two main conclusions. One is DC is an enabler for the energy transition, for the electrification of our energy system. It relieves the AC supply grid, and it's inherently uninterrupted power supply by including storage, be that battery or capacitors. And it is an improver for resilience, as mentioned, with local energy generation and storage. The second event is, I think, annually another acronym, EU-SEW, European Union Sustainable Energy Week. It's in the heart of Brussels, where we sometimes see on videos or television, whoever watches that still, the center of Brussels. More than 1,000 people, 3-day workshop, a lot of sessions. And there were a lot of sessions covering DC. I was there speaking in one of the industry panels, electrification of industry, it was called. I felt like here, like with people who already know about this and improve it and apply it. Also in what the European Union calls energy communities, which means you are permitted to exchange energy beyond your meter, beyond your connection to the utility. Typically, it used to be, okay, your utility gives you power and you do with that what you want to do, but don't go outside. This is scrapped. You are permitted to share energy, electrical energy beyond your meter, and there have been many examples shown, most of them in the Scandinavian countries. Since then, I've learned there's also many other countries where that is done, and much of that is also done in DC connections. Just last month, we worked, and Yannick, you're also part of that group, and created a promotional video. For the sake of time, I'm not going to play that. It's 2.5 minutes. Scan the code or get to the website. DC4EU is where you find that video. It highlights the DC as an enabler for the electrification, and also shows that, as you all know, it's nothing new. It's pretty much everywhere in the electricity system. By the way, will those slides later be shared with participants? Yeah, then you can also find that there. And there's 2 documents that the low voltage group is working on. One is, if I may call it, more on the social aspects of electricity, health, safety, environment. Key message is it is safe, it is good, there's nothing to be worried about. And the second document is a description on how low voltage DC microgrids as a industrial or commercial or other, let's think of shopping center with EV charging stations, contributor to grid friendliness by not needing peak power at every millisecond that you need it. Think of an industrial welding application. They need that peak power right now. And now we get it from 200 kilometers away from the power plant. DC microgrids get rid of that. In my second talk later, I'll show a little bit more about this. You provide that peak power locally, don't have to transmit it to a long distance and don't have to wait your connection to the peak power, but to your average power that you need to run your operation. And with that, I hope I've maybe made up a little bit of time. This is my contact information. I do work for Eaton in Bonn in Germany, have that role of chair of the Open Direct Current Alliance, and in this capacity here with the European Union set plan DC technologies. And I welcome some questions.
Yeah, we're almost on time, right?
Yes.
So
Yes.
same story. So we have time for one very quick question, I would say. But Harry, is not you this time, right? So
Anyone?
in part, this event is for the students. So I expect to see some questions from the back, right?
Yes.
Whoever captures the mic.
Yeah. Yes. Okay.
Okay.
Well, like
Harry promised to save the situation.
Yes.
Yes, Harry, please.
Hartwig, because the plan is next year that we will start a new program for physical the energy communities, this program. So I think that is a big chance for all the universities to be involved, and particularly grid operators and countries. Because maybe to highlight one thing, in the requirement there is written that, that that you shall incorporate the regulator to give permission to come to these kind of architectures. And this is one of the biggest challenges. And that's why we need a lot of preparation time to start far before the official request is done to the EU. That I want to highlight.
Yeah, yeah.
That's
Yes.
an important one.
Yeah.
But I guess Estonia is doing well. So we are already on the map of DC actors, right?
Yes.
Absolutely.
Yes.
Thank you.
Yes.
Thank you.
Yes.
Thank you, Hartwig.
All right. Well,
Yes.
thanks, Dmitry,
Yeah.
for the opportunity.
But this is
Thank
just
you.
your first speech out of two, right? But the only cup for you. It's for you.
Yes. Yes. Thank you very much.
Thank
All
you.
right.
Thank
Okay.
you. And we are wrapping up this session,
Yeah.
this set of talks related to politics, decision making, and things like this about that. Now we are moving toward business cases. So DC is everywhere, as Hartwig mentioned before, and there are a lot of business cases all over the Europe, but mostly in Netherlands, right?
Yeah.
So Netherlands is leading the DC innovation in the world, but Estonia has to do the same, right? In the near future. So I have to learn from these guys, and this is why we decided to bring in this section with experience from our Dutch colleagues and friends. So, but Hartwig, you. Okay. So, Harry, it's your time. Okay.
1 hour, eh?
No. This time the rules are a bit different.
Okay,
So
okay.
15 minutes for everything, and basically 12 for speech and 3 for Q&A.
Okay.
Not 16, not 60.
60, no, exactly. Language issues.
So during the lunch we can talk about different things, right? But today, now 12 minutes plus 3 for Q&A. Thank
Okay, well, that's incredibly challenging. 12 minutes because I prepared 1 hour. So, can I show the slides? Okay, because I first want to introduce Current OS, what it means, Current OS, because Current OS is a really beautiful organization that has the target to harmonize what is going on DC, because we talk always, we have an AC system anyway, so why should we? But if you look to harmonization in AC, it's far, far beyond compatibility. Because if you travel in the world, if you move everywhere, and even in regions, you have different grid codes, everything is different. So the interoperability in AC is far, far behind. And if we live in a global market, if we live in a continent-wide organization, then we need harmonization on electrical distribution. And that is why, for example, the USB-C is already by default the most, it's the old presentation, by the way. Is that, because it starts with current West slides. Yeah, it's the old one. You have to change. Because I was not prepared to introduce current West. But anyway, I want to tell that USB-C is just a perfect example of harmonization, because that is already worldwide the most standardized plug that exists. And technically, there are already today more USB-C sockets available than AC sockets of the same type. So that is one thing you have to put in mind as an example. So first of all, current West. Current West has the same task what we did for USB-C, we do now for the electrical distribution system. And to achieve that goal, you need to have partners. And on the moment, we have 114 partners already up into current West, and we expect the target of at the end of next year to have 200 partners. And this is on the global level. That means it's not a subsidiary company organization that is there. It's on the high level. It's signed by the board. So this is important to understand. And we really want to make one big family where we work together. And what's important to tell is that all the information, all the technology in current West is not based on sheetware, but it's based on hardware. That means it's physically built. We got the live experiences, we validate it, and the information that is validated is contributing to what we call the SRD, the system reference document, what describes. And by the way, if you want to create interoperability of the document, you need to do a lot of other things than only to make a system document. You need to make product specifications. You need to make a lot of things to work on that one. And that's why we have the gains, the big gains for what we stand for in DC is energy efficiency. It's nice. DC systems can support higher power because of lack of power, because power is the most expensive part in the system. So if you get more and more renewables, energy will go down and the subscription cost will go up because that is based on power. So to be power safe, it's incredibly important. And very important is that from a resilience point of view, you get a seamless transition from island operation or grid connected. There is no interruption, so that makes the reliability high. And the power efficiency is one of the big drivers there. And in current West, we have a lot of rules. So current West stands for current operated system. And that means we have a physical rule how to deal with currents into a microgrid. And that is based on a voltage band, distributed control, and isolated everything what is there on the technical stuff. And this is very important to find consensus about, because this will make a system. And important is to tell is that we have a lot of working groups, and that's why Taltech is current West member. So please send people in the working groups in a way that you can contribute to work together with all the big leaders in the world, work together on a common system that is there. Okay, then I will go to my presentation, and DC is fun. I always say, yeah, it's because it's nice to do, because all things we like are DC, and all the things we don't like are AC. That's you have to remember. So a little bit about this one. Now this one's already, and I want to highlight one slide. So my presentation will be available afterward. There's a lot of information on it. Every slide you can talk 1 hour on it, but this is for me the big driver, because electrification is a super good plan to do, because it really brings down the need for energy in a huge reduction, because technically if everything goes electrical, you can save 50% of energy for the same use case like in households. So this is important to understand. And other topic, mostly people talk about AC and DC and to compare apples and apples. It's wrong. If you talk about AC, DC, you're comparing apples and passion fruit. So this is different. And the difference is really that the systems are complementarily. AC is a centralized market where everything is based on the market, and then you have these headaches of capacity and congestions. DC is a local market and the power limits. So there's a lot of things there, and you have to dive into this one because this is really the most important factors why you are motivated to move to DC. Because it's not a DC don't want to kill the AC system. No, DC will support the AC system because they are compatible, and that's why they are passion fruit. Another strong message to make is that we are so dependent on electricity, we cannot live anymore without them. So I want to say the new engineers, the new electricians are actually the doctors of the society to keep the people healthy and clean. So this is one thing you have to look into. And the other statement I want to make is that we get more and more a responsibility as engineers. It's that in the past we make technical toys and we help the people with technology and we make economy with it, but now we become part of the human. Technology is more and more into the people, and that's why I have a new responsibility. And this part is not well educated yet. What is the responsibility of an engineer? To be human friendly and to be supportive, to help mankind to move forward, to survive. This is a very important one to consider. And one other point to consider is that this is a very horrible one because we all the time talk about energy transition. But today, if I say it negatively, I'm a positive person, but if I say it negatively, the energy transition is a chain of disappointments. And this is very, very hard to get because once you get the people motivated, people start to talk about, I like this diesel car, I like this V8 car, I don't like electric cars and all these kind of things. You start to polarize. And this is one I think I want to highlight because I already heard that people looking to the business cases of DC. And I can tell you that if you talk about AC/DC, you only talk to 1% of the society because they know what's behind the socket. And now we're discussing the differences. But we need to communicate to 99% of the society. They don't know anything what is behind the socket. And that's why we have to come to the social aspects, the most important topics, because there is the business case and the value proposition for DC. And that's why if you look to the society today, you see a lot of things changing. In the old days, everything was fair and equal. If you have a big house, you pay more. If you have a small house, you pay less, etc. But today, if you have a big house, you pay less. If you have a small house, you pay more. And that is actually makes this energy transition negative. And DC can repair that. So mark my words on that one. So that's why you see today people with a beautiful Taycan can charge at home. And people with a smaller car, have to charge on the street, pay 60 euro cents per kilowatt hour, while the other one is paying nothing. And that's not fair. So this is one thing to do. And this is one of the main drivers where DC comes into a microgrid approach to help the society and to communicate to the people who don't know what's behind the sockets. That is one thing to understand. And to introduce this a little bit more, I introduce very simply, I will keep it short, but most people know it, I introduced the world in 3 families. Family with a sailing boat, most likely entrepreneur, and I call them failed criminals, because entrepreneur, failed criminals is the same. Families with a motorboat are mostly succeeded criminals. And the people without a boat is actually the whole society. And all the time when we talk about the renewables and we talk about energy transition, we talk to the family A, because they are the ones with electric cars, they are sustainable, they have the big houses, they have the solar panels, they have the batteries, they have everything. But it is a small part of the society. And that we have to keep in mind. And one thing we have to keep in mind, we mostly talk about digitalization. If you look in the EU discussion and you talk about the energy grid, it's actually digitalization the grid. Now, there's one rule in system engineering, don't mix systems, because then you don't know which system is responsible for what. So today we start to digitize to control everything from the cloud and to control. And then we talk about cybersecurity. And if I reverse the question, and this is, most people maybe know this one, but if you're sitting in a car that drives autonomous, and this car is full with sensors, and it's communicating to the internet is communicating to a cloud somewhere, China or whatever, a cloud, where the decision is made. Okay, shall you brake? Shall you go left? Shall you go right? And then communicate back to the car and then control the car to take that action. Dare you to sit in a car like that? Me not. Because there's always somebody who don't like me and say, okay, oh, he has to go right. No, okay, now we go left. Poof, it's gone. And so you become vulnerable. And when your life is directly attached to it, you don't like the system. But if you look back to the AC system, this is exactly what we're doing today in the AC system. And if our life is depending on it, yeah, why do we do that? And because we have to do that, because there's no alternative in the AC system. And that's why it comes in. And that's why DC comes in. And I want to demonstrate a little bit the family house, what I call the Muse project. It's my private house. I'm just a family A person. I'm an asshole, how to say, or asocial. Because I don't belong, because I don't respect my neighbors. It's not true, but anyway, I will help them. But that is what the effect is. And one thing to consider, if you come to energy neutrality, if you come to 100% renewables, you don't have an energy market. And that was my question to the previous, is if you base all your energy system on the market, you will end up in a disaster in a way, because there is no market demand anymore, because the prices are by default negative. And that means you have only investment. That means you come to a fixed model and a capex model to survive. And this is a little bit to explain the house, but it is, by time I will reduce. But one thing I want to highlight in all the projects you do on DC is the biggest challenge is that every column is vertical optimized. So electrician optimized vertical, the HVAC organization optimized vertical, the air ventilation optimized vertical, the constructor optimized vertical, but nobody is make horizontal optimization. And there's a huge gain. And that's why I think the project with the housings is super good, because you have to look to multidisciplinary topics to optimize, and you could save a lot of energy there. And important, remove the user from the energy management, because most people don't know what energy is, so you should not incorporate the user there. And this is then the house to explain, but this is really, I'd say, an asshole house. Anyway. And why DC matters in this case, and why standards are important, is the ILC is one of the most important topics. I will explain later what is there. But this is the work that's going on in the IEC, where DC takes a quite mature position today in the number of standards that fully incorporate DC. And this is important because it was a huge lack and a huge amount of gaps to actually build DC. And this is the voltage, okay, that's for study. But this picture I like to highlight. We all love cooking, and we all love, maybe if you have the space, you have your own garden with your vegetables. And if you imagine that you are in the system and you have a garden, and you want to introduce your your tomatoes you grow yourself, you have to put in the tube. And then there is mass production of food somewhere from the Netherlands, from the greenhouses, what is maybe not that tasty, but anyway, it's also put in the tube. And if you want to make a plate, how sure are you that you get your own vegetables from the tube? And that's why the interlink converter comes in, because technically you want to lock and you want to bring your food to the fridge and cook your own food. And if you want to order a pizza from external food, okay, it's a decision. And that is why the interlink converter comes in, and that's why the car, that's the car example still, is that if you want to drive autonomous, you want to have local control, local management. You don't want to have global control or global management. And that's why you're there to sit in the car if the decision is taken in the car to move in the right way. And that's why the interlink converter, so this is a little bit technical, but anyway, this device is your front door. And there you can control what happens to your system or what happens to the external system. And this is a part that should be taken by the regulators and should be taken by economics affairs to force this device, because this is a critical part, the same as the data router in our mobile network. We need to get this high attention to it. And this is helping. And interesting to see is that if you compare the AC version of this one, and you have a battery, you have PV, you have an EV, and all connected by AC, you will roughly connect 37 kilowatt of power to the AC grid. And you try to optimize to stay in your capacity. While in the DC case, you can optimize, for example, with a 4 kilowatt or 3 kilowatt converter to the grid, and then you don't create headaches for the grid operator. But you can still increase your power here and have the freedom of operation and to have your full privacy. And in this case, you can completely disconnect from the cloud management, and you can avoid cybersecurity issues, and you can avoid privacy issues. And if you take that on the bigger scale, so this is really things to study, because the optimization is not in the house. The optimization is in the community. Because if you have more households, you need less batteries. If you have more houses, you need less PV, and you have a better utilization of the equipment. So this is what we call the second grid. And this is really the example of the distributed sources. And this was the missing link in standardization, because in AC, everything was based on a centralized point, centralized panel, and there you go. And here you go, distributed. And this is why the DC comes in incredibly helpful. And that you can bring to the higher level. And this is where DC comes in to make robustness. Because if you create what we have on the HVDC, the interlink between the countries, you can do that on medium voltage, and you can do that on low voltage the same way. And then makes your system resilient. And in the case of an outage of the AC system, you can maintain services in the village level, in the location level. And this is incredibly important, particularly in the program when we have so many angry people in the world who want to do something bad with us, whatever. And that's why if you look to the community, and if you look to the community on DC, it can look like this one. And that's, I think it's incredibly helpful, because there DC brings this harmonization and brings again back fairness. So this bad person, what you saw in the first picture, the family A, is now upgraded to family D. So the family A and C were not very happy together because they start to polarize, and the family D and C start to harmonize. And this is important to understand. And I have a big poster, and this big poster you can it's available for 100K, but if you publish it on the internet, it's free. So anyway, I want to thank you for listening to me. I hope I stay in time.
Almost. So thank you very much, Harry. So I think we can raise one question. Any of you? Lauri, but you need to come. So our online audience can also hear your question.
Thank you. Thank you for the nice presentation. I mean, I have heard several times about this kind of, let's say, concept for the DC grids. What would they enable? And it was presented here also that DC grid would enable higher power throughput.
Yes.
So how could you explain that one to me when I would be a house owner having a wiring rated at 16 amperes?
Yes.
So how could I push more power for that?
Now, because if you go back to this picture, because the grid connection is now based on your average energy that you need per day divided by 24. So if your household needs 24 kilowatt hours a day in a minimal energy to survive, you can connect to 1 kilowatt. And this converter makes a complete separation of the two systems. And that means, of course, you need to have a battery, but not the battery don't need to be big, because you can share the power on the loads. That's what I'm doing in my home project, is that the HVAC, that is why the horizontal integration, the HVAC shall be integrated into the power system in that way, because then when the sun is shining, okay, you can preheat your floor and you can store the energy. You can bring it, maybe some leftovers you bring to the battery. And this is based on the voltage level, so you can do what the capacity, what you want. So technically, like in my house, I will have a 1 kilowatt converted to the grid, and I will have 22 kilowatt to my kitchen. And the kitchen doesn't take so much energy, but it takes a lot of power. And normally you need a house like me need to upgrade it to 3 times 35 amps. And I can now go to two-phase 4 amp. And this is because of the help of this converter to separate. So this is really your front door. So you can keep the outside in the outside system outside, and you keep the internal system. So you redefine the system. And today in AC, we are part of the same system. So the cable is transparent connecting into the house. And then you have to manage your capacity. There's a lot of control, a lot of management to simulate normally on the 15 minutes base your energy, but this one is real time in power. That's on the technical explanation. But for the non-technical people, you have to compare it like your iPhone. It's in your device. It's in your private boundary. It's there. It's you. So you know if your solar is shining, the sun is producing, your solar system is producing energy. You can charge your car. You know there's zero energy coming from the grid to the car. All the energy is coming from the PV to your car. So you can ensure that the power flow in this installation in private space remains your power flow. And then you can choose to take power from the grid, yes or no, depending on if there is still a market model, still a marketplace or not, or is there a capacity tariff instead of an energy tariff. These kind of scenarios doesn't matter, but because here you can optimize the impact on the society. And this helps dramatically to save investment on the AC system. Because this is the issue in the Netherlands, because in the Netherlands we invest now 200 billion euros to try to fix the capacity. It's not enough. And that means the subscription cost will go for 400 euro a year for a household, will go to 1,400 euros a year. So that will rise 1,000 euros because of this investment. And if you have done it in this way, this investment was not needed. And this is one thing that is also important to understand. Is that answering your question a little bit, or?
Yeah, thank you. I think that part of those things that you discussed, I could discuss maybe further later. Kind of legislative issues there.
Yeah, there's a lot of regulation topics on this point, because this device should be recognized by the regulator to correctly define that device in the political area. So this is really my call to the politicians. Please recognize the interlink converter, because it's really the most beautiful device we have on this planet.
Thank you.
Yeah, Harris, thank you. And yeah, thank you very much. Let's make one photo. Oh, hand it over back to Hartig. Yeah.
All right, thank you. On some industrial applications and also on the Open Direct Current Alliance, one of the higher executives in the company that pays me said, when the new technology is introduced, it's good to have more than one entity promoting it. And that is what Open DC Alliance does along with Current OS and other organizations. It's better to have new things explained and promoted by more than one voice, similar to you don't want to have a single source supplier for running your factory. I'll talk a little bit about the alliance that I have the privilege and the honor to represent as chair of the board. Main part will be the industrial applications, where this has been invested with real money from real companies and proven. And I'll close with benefits and a brief outlook, where I see also low voltage DC playing a larger role. The Open DC Alliance is an international alliance. We're 3 years old this month. And we have a very dedicated main staff, 3 full-time people and 2 part-time people who are paid by the alliance members. We're all contributing, and they speak only for the alliance. They're not part of one of the members. We're looking at electrification and specifically DC as part of a sustainable world. And we work together with our partners and with our members towards a DC ecosystem. One of the things that we do is we publish documents and we go to events, speaking here and in other parts. What you see here is the result of more than 7 years of research, application, rigorous validation of DC microgrids in industrial and academic settings in 2 projects with more than 45 members. That was based in Germany. That's where also the base of the main office of the Open DC Alliance is. We created a system description, everything from voltages, electromagnetic compatibility, protection devices, you name it. And that was adopted by the German National Standards Body without changing a single word as a pre-standard. That has been used by the industrial application that I'll show in the next slide to get the, if you wish, the green light from utility, regulators, and insurance companies. The other part that we're doing, we're not just speaking on events like this. We have been in, I believe it was 8 international fairs where we have our own booths, where we talk to people that otherwise don't come to presentations or events like this to promote the story of sustainability and the contribution that direct current can do. On the industry applications, I have 3 prominent examples. The first one I'm going to show here is in the western part of Germany, a company called Phoenix Contact. They are a privately owned company. I think they have roughly 3 billion euro annual sales, and they built a completely new factory building that you see on the right-hand side here. They call it the All Electric Society Factory. It's all electric. It's largely DC, not only because they have also moved some of their existing production equipment there. And when you move, you want to keep things the same and then do the conversion step to a different energy source in the next step. You see the dimensions. It's not a small hut. It's a large scale. And this building with large PV on the roof and also on other spots in the area, actually on an annual basis produces more electricity than it does consume. And one highlight is they also have a seasonal energy storage. Like we all know, battery storage and capacitive storage. Capacitive for very short-term peak power, battery for hours, maybe days. The thermal storage stores energy from summer to winter and back on an annual basis. How does that work? It's basically a large water tank buried in the ground. It's basically an underground swimming pool, if you wish. I think it's 1,500 cubic meters of water. And it uses the phase change energy of ice to water and back as storage. So it's basically kept at 0 degrees. In the winter time, that water basin is the energy source for the heat pump to heat the building for process heat. So the water slowly starts to freeze. And in the summer, it is used for cooling the building and for storing excess solar energy that is not needed to melt that ice again. So for when you have an ice cube at 0 degree centigrade and melt it, the temperature stays the same, it stays at 0 degrees. The energy you need for melting that ice cube or liter of water or whatever metric you want to use is the same that you need to heat water water from 0 degrees to 80 degrees. So it's a large energy that is used in that thermal storage, and that's what they have implemented there. Second example, Mercedes-Benz. Many people know they make cars, and their largest building on the site, they did not only implement it in their production facility, the main part is the building infrastructure. They also looked at, think of a factory, where does the energy go? What is it needed for? And actually more than half the energy in that factory is not used for production parts, but for the building infrastructure, for heating, lighting, and it's efficient lighting. It's LED, it's all top notch. So they have also decided that low voltage DC will be the standard worldwide for factory automation and building infrastructure. It will be in effect 27, but suppliers need to have devices ready for the testing phase that is ongoing. So that's going to be a big boost for low voltage DC. And on a high level, actually the first DC factory was company Schaltbau. They officially opened that building. As you see, it was on a green field 2 years ago. Production, logistics, testing, and office buildings. And in those 2 years of operation, they have shown some really impressive numbers on savings. Overall efficiency gain is 15%. The peak power reduction, the connection load to the grid is 30% lower than if they had done it the traditional way. It is, again, an all-electric factory. You see some metrics on the right-hand side. And maybe the most important number for non-technical people is the next one. The energy bill is 1/3 lower. Do we need to talk more if that's not convincing enough? One highlight in that factory is the automatic storage and retrieval system, a high bay warehouse that is fully automated, runs completely on direct current, and it needs a lot of energy when those little wagons are moved up to put stuff away. And when those wagons are lowered down, they break and generate energy. And that is the connection power for that high base storage is 85% lower in the operation. So impressive numbers. They've been running this for over 2 years now. And with that, I come to an overview of some more benefits besides the ones that I've shown here. The example from industry. Breaking energy anywhere where you have moving masses, be that robots or be that storage systems. In an AC system with the motors that are, most of them are driven by frequency inverters. In AC, when they break, they burn the energy in a braking resistor because the DC-AC part is a one-way street. You cannot supply energy back to the AC grid. In a DC setting, we have the DC bus where the energy can directly be used and recuperated either in the next robot or motor that needs it right this minute, or can be stored for later use. So depending on how much movement you have in your system, how volatile electricity demand is, that is a large saving potential, and that is what contributed to the energy efficiency gains that I showed in the Schaltbau slides. And oftentimes that heating resistor, I have been talking to a small, medium-sized manufacturer of machinery. They have a large energy demand or a large energy demand from those braking resistors. He said those things are burning literally, not literally, but figuratively, the energy off. And most of the time in the summer, you also have to cool that away. So it's a dual saving. In a nutshell, like we need fewer stuff. We don't need the AC-DC conversion. We go basically without a detour. It's energy efficient. Depending on your volatility of your system, it's 10-15%. Of course, we can integrate photovoltaics directly without detour of converting it to AC, transporting it 50 meters down the hall, and then converting it back to AC to DC. Resiliency aspects we have already covered. And of course, peak power reduction, the benefit for myself and for the larger community is good for both. To the outlook, my last technical slide. 10 years ago, when we started with direct current, it was industry, it was manufacturing. What has really taken off is data centers. I see that in the company that pays me. Since the beginning of the year, I don't have to go and say, okay, DC is good and come on and come on and come on. They come to me and say, oh, why don't we have those breakers for DC? Because the Metas and Alphabets and whatnot come and want that. Data centers have seen that the efficiency and the resilience gains through DC is a real game changer. And the Open Compute Project Foundation is, so to speak, the hardware foundation for the data centers. They have adopted the open source principle from software to hardware, that it's kind of an off-the-shelf universal solution. And currently, again, with contributors from CountOS and ODCA and all the data center operators, there's a sub-project underway for specifically low voltage DC power distribution in data centers, starting at the medium voltage supply side, connection to the utility, solid state transformer, making direct current and transmitting that through the what they call AI factory right to the compute rack. And prior to the last OCP World Summit, NVIDIA, the chip manufacturer, published a white paper specifically going to that low voltage DC supply in the factory. And the stock number here, quarter less space needed for the electricity distribution stuff. So you can focus on using your space for the actual computing needs. And with that, you've seen this slide. I'm looking forward to some questions, and thank you for your attention.
Thank you, Hartwig. Again, I guess we have one question. Let's maybe go with Arshad then.
First of all, thank you so much. It was very insightful presentation. And I know there are experts from different industry, and I believe I will be one of the kind. I came here for aviation, especially Professor Andre and Professor Dimitri knows me. It's been a couple of months. I'm very active with the university because the field we are usually work with airports. And as you mentioned, different type of infrastructure. So airport is one of them. And especially across Europe, we see a lot of development in airport. We see US is a huge market, but what I'm more interested is a region which is currently fast developing in terms of infrastructure, every type, but mostly for aviation, which is Asia and Middle East. We see a lot of airports coming up. The DC airport, or you can say completely solar power airport achievement we saw recently last year when Red Sea Global Airport in Saudi Arabia was launched and is completely working on renewable. If you see the structure, it's a marvel of engineering. And now more and more big stakeholders like GMR in India or Adani in India, they are looking for such infrastructure in terms of airports where they can have smart airports in terms of DC, of course. In aviation, and not only the infrastructure of airport, one compact size, but in terms of whole aviation is built on an agenda. We need to reduce the size impact. It's the aircraft itself or it's the equipment on the airport. So my question is that I believe the universities or yourself covering a lot of different sector. If you have any projects where you would be coming into the area of airport development or airport infrastructure, I would be happy voluntarily work with you. I respect the universities, I respect the professor, and I believe everyone is doing a great job and being from the industry. I would be happy to be part of it. If there is anything that you are doing with airports, airport infrastructure, I would be happy to work with you. And thank you so much. It was kind of confession, I would say, another question. So thank you so much.
Okay, well, thank you. Well, basically, all of these benefits apply not only to industrial or commercial supermarkets, applications, data centers, but for airport as well. We had within the Open DC Alliance also contact with airport infrastructure, but we can talk maybe during lunch and get to that. I saw a question back there or a couple.
No, you know, we are severely over time, so,
Yes,
but let's move the discussion to
I still talk
lunchtime.
shorter than Harry.
Yes, so that is true. So thank you very much, Hardik.
Yeah, we'll get to the questions later. Thank you.
Yep. And the next presenter will be from DC Systems. I would say probably the first company in the world to start building DC buildings. 5 seconds.
Yes. All right, maybe I can start already talking. Do you all hear me?
Yeah.
All right.
You're on.
No. All right, I need to get the mic closer. All right, so first of all, I would like to thank Andriy and Dimitri for the invitation. I'm really glad that I was able to join today to this fantastic workshop. I also learned a lot today and I'm looking forward to the next presentations. My name is Vicky Makridou and I'm here representing DC Systems by Schneider Electric. It's a company located in the Netherlands, but we are, of course, addressing projects globally. So today I'm here to discuss about powering the future with direct current. And first, let me introduce you my team. So we are a team of 25 professionals, as I said, based in the Netherlands, and we cover different expertise from engineering, manufacturing, business development, application, of course, marketing. But we are also providing customers with custom solutions and the products to complete the solution. We are experts in this field in AC/DC microgrids. We were founded in 2009 by Harry Stockman. Actually, he's here with us. He presented earlier, and through the years we started implementing first some research programs funded by the Dutch government, and later on we started with commercial projects, and this led us actually to the acquisition by Schneider Electric back in 2021. And we are also very active in IEC standardization bodies, because this is also one of the challenges with DC. Now, let's take a step back, and I want to show you this slide actually to reflect a bit of how electricity distribution was in the past and what is changed is different today. So what is the action that we need to take? So here you can see that energy distribution was largely linear in the past. So power was generated in the main power plant, coming to substations, and then reaching to commercial areas, residential, or the industry. But actually today, with the energy transition, although that previous system served us in the past, today we see that the energy landscape is changing dramatically. So we have an explosion of electricity demand. Think of the increase of population, for example, but also think of electrification of different sectors like heating or cooling that was not electric in the past, but also electrification of mobility, for example. So with all this and many electric loads coming to our lives, we see an explosion in electricity demand reaching up to 80%. But not only that, we all face climate change and we feel the need to take some action. So we are trying to decarbonize our installations to become more sustainable, but also to save some money from our pocket, right? And with this, we invest in renewable energy. And we see renewable solar panels or wind farms like popping everywhere now, also in our in many homes. But all these changes actually affect the energy landscape. So it looks so much different than it was in the past. So right now you can see that we have local generation of energy, not only energy coming from the power plant, but also everywhere in the system. We have also storage. We have also the possibility to send power back. And this is affecting the system, making it more complex than ever. And with this comes some problems. And I was glad to hear that Estonia actually joined the European grid, but I hate to break it to you, but it comes with some problems. And you can see here, I think Hardvik mentioned it before, we also have the problem of grid congestion. So think of grid congestion like traffic in the road. So it occurs when too many cars try to pass through the same road. And so it's actually a distribution problem of electricity. You can perhaps build a new road, you can lay a new cable, but this requires a lot of money investment. So it's not that easy to solve. And in the Netherlands, because the grid operators have always been transparent on this topic, we know that right now there are 14,000 requests for a grid connection that can result up to 5 years of waiting period. In other countries, they are not so transparent about it, but we know the same issue exists, like in France, in UK, in Germany, and so on. I'm not so sure about Estonia, but maybe I can get your input later. And also we have an increase of energy prices with the expectation of a 4 to 5 times increase of energy prices. And this is also due to the grid expansion that is required to support the energy transition. So what do we do? How do we solve this? Now, some solution that has come up, and it's behind the meter solutions, as we call them. These behind the meter solutions actually it's a solution that you can actually do here in the very last end in the low voltage area. So not here yet, not here, but in one building, for example. So this solution can run independently from the grid. You get your grid connection, it comes in your electricity panel, and then you create your own system with solar, batteries, and you connect all your electric loads. And in this way, you can be independent from the grid. So if there is a blackout in the grid, you can actually be still resilient. You can have more capacity in your system. So you have like 50 kilowatt grid connection, you get another 50 from solar panels. And if you store the energy overnight, then you also can have lower prices. But is this enough? I don't think it's enough for like many businesses, for example, or for the industry and so on. So because actually here we're talking about an AC architecture, right? So we get an AC connection, AC architecture, but if you see all the loads here are actually DC. So we have solar panels that generate power on DC. We have batteries that store energy in DC, lighting, LED lighting is native DC, and all your power electronics, heating and cooling. So in this, in this topology here, in this architecture, we notice actually that we lose a lot of energy in conversion. So in every step of conversion from AC to DC, you lose energy. Not only that, but even though you get some extra capacity in your system through the solar panels, the grid does not allow you to exceed your grid connection. So if you have 50 kilowatt grid connection, your capacity in the system has to remain double that, so 100 kilowatt. So it's still, a limit from the grid. Then you can imagine that all these loads and sources are very difficult to control. So it's not that easy to decide when to charge what and so on. And it's very complex to scale. So if next year you decide that you want more EV chargers or more solar panels, then you have to lay a new cable. And now with this comes the solution with a DC architecture. This is what my team is actually working on for the last years. And with this solution, we have noticed that if you connect everything in a DC with a DC architecture, then you get reduced grid reliance. So you're not limited from the grid to have like double the grid, double the capacity in your system, but you can go higher than that. You can go up 3 times, 4 times, or the sky is the limit. There is no limit then from the grid operator because you are very well separated here. And I will show you later the product that can help you with that. Then you have enhanced sustainability, and with this we're referring to energy savings. So we have noticed from projects up to 15% energy savings and up to 50% savings on copper. Because here you can see that we talk about a decentralized architecture without many cables. It's very easy to scale as well. So if you want to expand, you just add one more cable here and you can expand the installation just like that. And it's very simple to control, simplified control, because all the loads and sources interact with each other thanks to Droop control by Current OS. Now, this architecture can be enabled with the products that we have created for this solution, actually. Here we talk about the interlink converter, which is your gate, the interface between the AC system and the DC system. This is actually with galvanic isolation and it's a win-win for both systems. The grid operator does not have to worry because you don't create any power quality issues for them, but you are also secured in case of a blackout. Then we have created protection for this kind of system, and this is very important because DC in the past was considered unsafe, but with the right protection, we can say that it's even safer than AC systems. It's a product equipped with solid state protection, and this can ensure a very quick trip of the breaker. So you have to connect actually protection everywhere in the system. We have also conversion devices to convert into different voltages for all the distribution in your home. Imagine that you want to connect, for example, your batteries, or you want to connect your laptop or phone. And with this, actually also like USB-C sockets and special converters to connect the batteries. So this is like in a big picture, like all our product offer with which we create this kind of architecture. We have actually used all the products to implement installations and projects worldwide. So you can see that we started from the Netherlands. Well, we have many projects there, but since the acquisition from Schneider Electric, we also expanded our operations worldwide. So we now have some projects in Korea, China, Bahrain, and the US. And we are actually targeting different applications, so commercial buildings, EV charging, public lighting, modular application, indoor agriculture, and so on. So here I have a few examples to share with you. This was the first actually commercial project of DC Systems. It's the Circle building in Amsterdam, one of the busiest areas actually in Amsterdam. And the problem there was, of course, grid congestion. So the customer could not implement the project unless they could create more capacity in their system. And with our solution, we managed to actually triple the capacity of the installation in order to cover the needs for all the loads. We managed that with solar panels. This solution actually did not include batteries, but we were able to integrate the solar panels easier and get actually the permit also for the from the fire department that it was a safe installation, and it was also resilient. And it was actually tested one time. There was an event and the blackout actually occurred, and the system actually remained on only powered by solar panels. Now we are moving on to more recent projects. So here we have a project in our own office in Schneider Electric in Grenoble, France. The goal there was to decarbonize the installation and use as much power coming from the sun as possible. And we created an installation with 6 EV chargers, lighting, and power coming from PV and battery storage. Now, this was a clear example of reduced grid reliance. We were able to operate only with PV and battery, and we measured 35% copper savings and overall efficiency. Now we go to the one of the last projects. This was a building example in Lille, France, and the customer challenge was there was actually to create a more efficient building and future-ready building. So this is actually a contractor in France, and they wanted to see what are the benefits and if they can recommend this solution to their own customers. And they measured actually that they were able to save 20% of energy and 50% reduction of copper. Now, this is very important because one of the arguments for DC is that it has a very big capex cost. And I can tell you that, for example, if you take also this into account in the capex phase, then you can see a balance between capex of AC installation and DC installation. And in the OPEX phase, with energy savings and other benefits that come with the solution, you can see that the DC solution is actually a better one. Now I want to go into the last part of the presentation and actually talk about one of the demo areas that we implemented. So you saw maybe earlier in the map that we don't only have projects, but we have implemented some demo areas around the world. And the intention behind that was actually to create a space where somebody could come regardless of their background and experience DC technology and think about how this technology, the potential that it has, and how it can power our future. So basically, the intention was to make it open as possible to address different audiences from electricians to government bodies, to be a space for collaboration, testing new ideas. We have also invited partners to participate and show their solutions. And our intention was to create like the perfect installation so that we can also influence the standards through it. You can have a closer look of the installation here. So it's a space of 300 square meters, 3 floors. And on each floor, we saw something different. So from how the system works and operates, how the different applications and how they're connected on DC, and also like thinking of EV charging installation office space, industrial space, data center room, vertical farming, and so on. And we also have a space dedicated to knowledge. So then people that don't have any background on DC can learn more, but people that are experts on DC can actually see how the system interacts with each other. And this is the last slide. And here, actually, I think from all this presentation, you probably understood what is the impact of direct current technology, but the technology part is not enough. So I wanted to invite you to also participate in our movement. And you have the possibility now to take a digital tour of the Direct Current Experience Center. So you can maybe scan this QR code and go to the dedicated page. But even better, come visit us yourself, see, experience it in first place. And yeah, you can contact us through this email and come.
Thank you very much. So, Hossein has a question. Come. Good. Students finally hit it up.
Thank you very much for the presentation. I have the question that I saw almost all big buildings, such as in ODCA, I saw some of the buildings had heating storage. So how you look to this matter in the residential building?
So one of the projects that we implemented was also residential, so the one in Bahrain. So there you install heat pumps. You connect heat pumps to the system, and I don't know if you have a more specific question on that. Like air conditioning or a heat pump for heating the house or the building can be integrated into the system. So today there are loads that are powered by DC directly. We have one example in our experience center actually. It comes from one company that is called Train. But there are more actually heat pump manufacturers that can have created heat pumps that operate on DC, and they are also on the Current OS Foundation. I'm thinking of Daikin. I'm thinking of like Heliotherm. There are many now manufacturers that have heat pumps on DC.
Thank you very much, Vicky. Applause, please. And the next
just one addition. The question was also about storage. The building use a lot of thermal energy. So thermal storage is a great substitute to batteries. It's much cheaper to store cold, like Ardvish mentioned, or heat in phase-changing salt. So I would say, and this is why heat pump manufacturers joined Current OS, because they understood that there is a value proposition in combining heat pumps with thermal storage to substitute batteries.
So thank you very much. So Vicky, also, we have this unique I3DC cups. One is for you. No, that is a Taltech one. This is I3DC. It's a unique. So, yeah. So Lawrence, building a lot of DC lighting in Delft and around the world. So Lawrence, the floor is yours.
Thank you. I'll try to do it quick. I'll talk today. We do all kind of stuff on DC, but I'll talk mainly. Oh, I don't. Sorry. Thanks. Right. Today I'll mainly talk about DC. Quick introduction, DC opportunities. We are also located in the Netherlands, like DC Systems as well. And we work a lot on DC, and we do that both on component level as on system level as well. So we really, and in that way, we can really change a lot of things and really get system level benefits because we are able to change the components. So we look into solid state circuit breakers, solar converters, battery converters, EV charging, all that kind of stuff. We also participate in international standardization, yeah, so far we have 24 kilometers of DC grid, low voltage DC grid in operation with our technology. When we talk about public lighting, initially we got into this. Obviously, DC systems, they were already there. So we were like, okay, we are not going to do the same stuff. So we looked into, okay, what's next? And we had here a question we started in the municipality of Zoetermeer. They were asking, hey, what can we do there with these DC grids more than just doing lighting? And this is an example of a neighborhood. In red, you have all the feeding points or grid connections for the public lighting grids. Green are additional cabinets where the cables end. And then the question was, hey, what can we do with this grid? So we looked into that. And then before there was also one question about the capacity of DC. In public lighting grids, stuff is a bit different than normal. Obviously, always DC is better in the usage of infrastructure and cables. But in public lighting, the special thing is that the grids, the cables are very long. So we did here an analysis and we looked into, okay, what are the limitations in power capacity? And here in these graphs, you see on the vertical axis the power that you can consume on the DC grid, and on the horizontal axis you see the length of the cable. And you have different limitations. The curved lines are the voltage drop that you have in the cable. This is now 5 to 10%. Basically, you see the longer the cable is, obviously you have voltage drop. At some point, you are limited in power. Then the purple line, straight line, is the current limit of the cable. If you have a certain thickness and thermal conditions, whatever, the current is limited. With the voltage drop, if the cable is longer, you're limited in power. But then in AC, there's another interesting limit that before we started, I wasn't that much aware of it, but it's actually the most significant one here. And that is that if you have an earth fault at the very end of the cable, you want to make sure that so let's say the wire touches the light pole, then the light pole has voltage. Somebody might touch the light pole. You don't want that situation to last too long, and there's limitations. In this case, 400 millisecond. You have to make it safe. In AC, when you have these very long cables, you have a lot of inductance, and that means that a fuse takes a lot of time to trip because the short circuit current is limited. And that means in the end, what they had to do in AC, they had to use much thicker cables in order to get low enough inductance, to get high enough short circuit currents to trip the fuse fast enough, so that it's safe enough in time. So effectively, you have a very high current capacity on that cable because the cable is extra thick, 10 millimeters square in this case. But you have to fuse it with a 10 ampere fuse, and then you are limited to like 7 kilowatts on that cable, whereas normally you could do way more than that. In DC, we do solid state protection. We don't have that problem. So that kind of limitation actually just doesn't exist for us. So we can really go to the current and voltage limitations that we have, and they are a little bit higher than in DC. But you see here, basically, you're just limited to 7 kilowatts. Over there, we can do at the beginning of the cable like 50 kilowatts. A bit further down the line, still significantly more. This is just a quick example for a solid state circuit breaker, bipolar DC grid, 350, 700 volts in this case, with a short circuit on the negative pole. And you see here we clear that fault we trip in 2.5 microsecond. And it is actually a 6 ampere breaker that was tested here. And the current only goes to maximum 2 times the normal current, only to 12 amperes here. Then we can go a bit further in this grid. They build the infrastructure in a meshed way so that the cable just doesn't go somewhere, but it actually ends in another cabinet. So you could also feed from the other side, mainly for fault scenarios that you can quickly bring the lighting back up. If we would use that in DC and say, let's use it in a meshed operation, then you can feed the cable from both sides. Then the scenarios look like here, and then you get up to 100 kilowatt of power in such a cable, which is quite a lot. And that means we could actually charge electric cars. In the Netherlands, light poles are here quite convenient next to the parking spots. So the idea would be to just put a double EV charger on each of the light poles, and then basically we could provide 50% of the parking spots here with EV charging overnight and charge like 40 cars overnight. In this neighborhood, that was then 1.4 megawatt of power that we can actually distribute into the neighborhood for EV charging. But that's all potential extra stuff we can do now recently, and I want to now come back on just a pure public lighting application because that's also interesting. We did here recently, well, last year actually, it's now operational since more than 1 year. We did a public lighting project in Delft with our solid state protection cabinet. And it's this neighborhood here between those roads. I want to quickly go through with you through this project. We have in this grid, because we are not limited anymore with the length. If you build new, so this is replacement. This was built in the 60s, 70s. Cables were old, complete replacement of the infrastructure. And then you have different choices. Then it's not, you have already cables, what can we do with it? But a new design, we can save actually materials. In this case, we don't have this length limitation, so you can go way longer. In this case, 3 kilometers per cable with solid state protection. In total, it's 280 light poles in this neighborhood. And then we can go actually to 2.5 millimeter square cables. So basically, you save 75% of copper. And then because the cables can be much longer, we don't need before they had, so it's very nice, it's actually one-to-one comparison. Before they had 4 grid connections, 4 cabinets in the neighborhood. Now we can do it with 1 cabinet because we can make these long cables. And so 75% savings on grid connections and cabinets as well. And additionally, we have residual current monitoring and protection as well. So this is how that looks like in practice. And the monitoring part, I think that's also a very interesting part. We had that initially already, the cable had been damaged by a fiber optic operator already. So we were able to detect the leakage current and then immediately identify that there was a fault and have that fixed. That's a quite important part, and that can be used for preventive, predictive maintenance actually. So you can see the leakage current in the cable. You can sometimes also you see it when you turn on the lights, when you put power on it, that there's a little bit of leakage, and you know that maybe there's some water in the cable. So you know that there's something going on, and you can investigate before the whole neighborhood is dark. A couple of weeks back, we had actually, that's actually interesting for us. We had our first short circuit in the grid. And obviously you do a lot of testing and stuff like that, but this is now in normal operation. So this is not pilot or something, this is just normal operation. In the middle of the night somewhere, there was a short circuit. And then I think this is another interesting part where we really see a very big benefit. And that is that we were able to isolate that fault, localize the fault and isolate the fault and have everything, all the lights back in operation within 2 hours. So that means basically, of course, this was at night and the policy is only we check next morning if it happens after midnight. But then basically within 2 hours, it was possible to get everything back to operation without digging in the ground or anything like that, because we use a ring architecture. So we are able to localize where it is in the light poles. We can separate the grid and then find that location again. So we have here this topology of this ring in pink. Basically, you go and split the ring in half, and then you can power up one half of the ring. You know if it's a fault there or is it in the other half, and then basically half. Further the grid, and then eventually here at this point was the fault. And that can be basically done in a very quick time, whereas in AC, because you want to minimize the cable length, typically you do underground connections, T-junctions. So actually, if you want to reconfigure your grid, actually you have to go in the ground, dig up the cable, and make new connections. So it takes days to find something like that if you have cable faults like this in AC. And that's actually a very big cost impact in terms of maintenance, because in AC, right, then the neighborhood is dark until you do that. Here in this case, we found a fault in 2 hours, and basically then the installer, they could just schedule in maintenance to dig up the cable where we knew, okay, between these two light poles, the cable is broken. Then they can just schedule it in. So it's also way cheaper because you don't need to do it the same day, basically. Now, very recently, we delivered another cabinet for actually a project where we there was already D-Squid. This was a replacement cabinet. Actually, this is very recent work. You see the cable state. It's not yet completely finished. But I want to very quickly show this. Here on the right side, you have in the light pole this connection, an example of this connection, how the cables come in and out. And you can basically at every light pole operate, open this ring. Here on the left side, you see this cabinet with our solid state breakers there. Additionally, there's isolation switches to operate safely on the wires. And this is right now, I believe it's the biggest low voltage DC grid in total, 16 kilometers of DC cables interconnected, only with circuit breakers in between. And that connects actually here also to we have here also solar and battery storage where that is feeding this grid when there's enough sun as well. Very quickly, I want to show you more of the monitoring. I think that that's a very important part as well, because you can really observe what's going on and do stuff. So for example, here we can see unbalanced power here at the bottom right. So you know, are there enough lights on the plus and the minus pole? It also indicates here, for example, you see some lights don't work properly, they switch off. You can go and investigate that and figure out what's going on there. Recently, we also implemented nice features like automatically switching on and off these lights. That was like an emergency thing that had to be done because suddenly that was needed. But for example, now our circuit breakers, they know where they are. They know when the sunset comes. So you can completely integrate the full solution into those products. And we also have energy measurements. So we know you can over long term see if everything is running how it's supposed to do. Does the dimming work how it is? Good. Then I want to end with this. Now my focus was mainly on really the public lighting stuff. I think the main message here is if we really go just for public lighting, actually the savings are enormous compared to normal DC. DC is always better, but in this case, we really have realized one-to-one comparison with what was before in AC, 75% copper savings, 75% cabinet and grid connection savings. And additionally, very important part is the monitoring for predictive maintenance, also adding a lot of value. And because we can make these longer cables, we can make different grid architectures and really go in and out with these cables, which allows us to find faults and isolate faults very quickly without underground work, which has a huge impact on the maintenance costs in the long term. Because in average, in these kind of grids, you would expect like maybe one short circuit or event happening every year. So that's quickly thousands of euros a year that you can save on that. And one message maybe in the end as well, we talk about lots of DC, it's all new technology, it's difficult. How does the business case work, payback time, return on investment? In this case, we don't have to talk return on investment or anything. Overall, for the whole project, it's just cheaper, actually. So we have so much savings that right now it's just lower investment cost. And next to that, obviously, you have maintenance and stuff like that also lower. So special case, but I think important message. Thank you very much.
Thank you, Lawrence. So as you can see, DC gets only better and better with presentations. So I guess one question we can manage. You need to come here. Whoever is first has a mic.
Thank you for this wonderful presentation. So this is a really big grid in terms of length. So how do you deal with this line losses or resistance in this in your system?
Yeah, actually, it is not a big deal because let me quickly show you here just this slide. You have here the currents. You see, we have 2 amperes of current in a 2.5 millimeter square cable. That's nowhere close to the limit. Actually, we could even save more copper. It's more just if you make very thin cables, it's kind of easy to damage. So actually, we are not even at the limit of the thing because LED lighting is very efficient. So in the end, in terms of power, you're quite good, and the voltage drop is actually not really a concern in this case. This is the last grid we just did. What you see here, we have 6 amperes per line, and that's in this case, I think it's 4-kilometer long cables. So we are not really at the limitation in terms of voltage drop. Yeah.
Thank you. So Lawrence, again, as a speaker, you get a unique mug.
Perfect. I'm Kai. I'm trying to present a little bit about the bidirectional charging as a way to come to the DC grid, because it's DC, and by using AC to DC at the end. That's also the questions that we are getting when we're offering these products. But I also want to start with the why DC. So I will repeat a little bit from the former speakers on that side. You know how the energy system is changing in the actual century on our side. So we are getting more and more renewables in. We are getting local generated energy, and we are getting local stored energy on that side. So the question is, if it's DC microgrid, which could be the answer to this, or a better answer than the actual AC solutions we're having on that side. You have all heard about the benefits of DC on that. So please, you will see different numbers actually. So it's general information that you see, okay, there is some benefits on that, like the energy savings we're having. What we are seeing also in small systems, but also in larger systems from that side. We will see that we could transform more power over the same cable if we want to, or we could do it vice versa. We could reduce the cable or having lower losses on it. We could have cost savings, like you heard, even more than this 50% what we have mentioned here in your installation if you're changing to a DC system. And it could be also save you cost and while you save space on the other side and not need that much equipment or cabinets for going there. So that's a good reason to change on one side. But what I also have to do with the EV charging, because we're also getting these benefits there if we are looking at charging installations. And there we're also seeing that you have your high power charging already is DC. If you're driving on the Autobahn, if you want to fast charge, it's DC. Because your battery is DC, and that's the easiest way to do. We are seeing that the bidirectional charging, actually, today, the common way is using DC to discharge your vehicle on that side. And you could also have lower losses because you did not have this transformation of the energy back to AC. DC allows even the reduction of the AC connection point that we also have heard that we have in some countries, and more getting some issues with the grid connection on that. We're also seeing that the installation going to distributed installations, so having not only one charger there, having more than one charging point, and then you need a way how to distribute it, how to make this installation, if you're having a power electronics at each stage, if you have a central installation, if you're using a DC grid at this parking lot, for example. And that's already happening. So not only here in Europe, where you find some companies who are offering this, you also find it, for example, in China. There are already installations which are working DC very small DC microgrids on this location, but also bidirectional, using batteries as an buffer for the grid installation, using solar that's there and it's working. But we also see it with low power installations. So that means not having high power charging on that side. We also going down. That's a product Ambibox is doing. It's an 11 kilowatt bidirectional wall box on that side, and you're discharging your car with it. That could be one time, but it could be also multiple times on a parking lot for the installation. And if you're looking forward, coming the next slides, it could be DC-DC, using your DC grid and using at your as your outlet, only such a charger on that side and building it up. And that's what we are doing also actually with the AC-DC version on that side, with parking lots, with large installations on that side, on factories, on public installations, to also supply. Like in the first example, it's a manufacturing plant where the EVs have to discharge before they're getting transported to a certain state of charge level. And you could use your energy back because you have charged it before into the vehicle. So you're getting more and more efficient in that way. The same we are seeing at home, where we are actually offering the AC-DC solution and going there, but the customers understand and asking why I could not directly connect my solar panels to it, why I could not connect my battery. That's real questions from normal people at home that they ask. Not skilled, not trained in that, but they understand that it's more efficient to doing it on the DC side than converting it twice. And that's a reason why we're also thinking, okay, where we want to go, what we have to do next. And that's it's coming more and more to do DC grids at home, at factories, at different installation sites on that. I think it starts in different ways. So for charging at home, it will be some kind of this hybrid inverters, which you are connecting all on the DC side and have a very local DC grid. But step by step, it expands to the whole house to coming there. So it's a short video what I want to show you on that side, because we also looked in that what's there, and you also heard that it's not only the battery and the solar what's there, but yet you also have the loads that are working DC. And we are trying to figure it out to test this. It's years ago, so it's not an actual one. And please don't do that things only at the university here in the lab and connecting or doing that way, but you're seeing that your appliances are working DC. I hope it starts. It starts, yeah. It's not that long. We tried it with Electrolux together and tested different applications and seeing, okay, if it's working to use and to go that step with this company to create this ones. So it's a lab case with 300 volt DC, and it was common devices from there. No modification. The devices was as they sold it. And they are working. So that's an air purifier or even the standard adapter. Yeah. Or the LEDs like you know on that side already. So it was a lab case, that's why I say don't do it at home, but they all worked in that way. That's what they want to show and test with us. The other things, you know, to going there, how to do it. And the last thing we did with them was a DC fridge that already in our lab, standard fridge, directly connected to DC and to soon becoming there. What's also needed around and what we are looking on these topics is to having the software to operate these different systems, to monitoring it, so that you could use it at home and seeing all the information to the system. Yeah, that's the fridge I mentioned. So it's also normal fridge what they are selling, and it's working DC directly. DC converter to get the energy out of a battery in that case, but it was there, and that's some years ago. So. But where we are now, what we are doing now, where we are looking. So I'm said we are not only doing the AC/DC, we also want to go the DC way. And that's why we also started the project to taking the charger, our bidirectional charger, and bringing it to a pure DC-DC device. And that's what you're seeing in this picture. We adapted to the DC industry standard in that case to fulfill the requirements on the DC grid side and connecting as a device. And you're seeing it in a lab installation where you have a small DC grid there connected. So the metal box, that's the charger. If it's not covered with any housing on that side, you're seeing an open charge controller there, and it's working. On the left side, it's our lab, so we're having more showcase installations there, and the white one is the DC-DC charger. It discharges real vehicles which are on the market actually. It's working, it's there, it's under testing already now, and we're looking how to go on with it then. But we are also seeing it in other applications which are coming on that side, where we're coming back to the pure battery in that case, and that's battery testing centers. They are already using DC grids because they understand it's cheaper to operate if you could reuse your energy on that side. And it's DC already. So that's huge installations where you see and where you could step in, like the data centers we have heard on that side. That's it. And the last one, it's not for me, but it's true. DC is the future. It always was. Thank you.
Thank you, Kai. Special thanks, since this is the first presentation in under 15 minutes. So we have one question, I guess. So whoever comes first can claim his question.
Thank you so much for the presentation. So my question, maybe it's that just I'm not clear about the understanding of this system because this is not my technical area. But then coming to this point after so many presentation, the DC-DC conversion that we are talking about, is it like the Ampy box, is it essentially two-stage conversion, like DC to AC, AC to DC?
Yes, at the end, sure.
Okay.
So for charging, and if you want to connect a vehicle, we need a galvanic isolated device. So yes, you have some high frequency transformers inside, depending on the topology you are using for that. And that's you're doing a kind of AC, and then you're going back to DC because of this high frequency transformer what you're having in.
So that means we're just shifting that. It's like shifting the location. For example, initially what happened is this OVC in car, which is essentially a converter, right? It was inside the car, so we plugged in AC, then we removed it from the car, brought it to the charger. It was a Hughes, then we call it DC charger. Then again, we shifted it back. It's like a pure DC. So it's something like we are actually taking it back location-wise from end product to maybe on the grid side or something like that.
Yeah, it's moving outside of the car. It's hanging on your wall. Somewhere there, you didn't use the onboard charger for that kind because you're directly connected to the battery. It's there, and yes, you're right. It's moved from there to this location.
So it's connected. I really don't understand. So that actually increases the efficiency of overall system.
Yeah, it increases because you're having one stage less in between. If you're looking to your whole energy system, you're not converting from the photovoltaics, for example, back to that. You always have some DC-DC converters inside to adapt to voltages, like we have seen also in the presentations before in such kind of system, but you're having one stage less. So you're not going to AC, DC, and back. That's all internal losses, and that's the savings what you're always seeing. This 15% or more of efficiency comes out of leaving the stages out.
Yep, that's it.
Yeah,
thank you.
Okay, I guess most of the audience is seated already. Those who are still finishing up their lunch, please join us as soon as you can. But we have to continue to finish in time. So the next presenter will be once again the representative of Republic of Estonia, and it will be Mikk Vahtrus from Ministry of Economic Affairs and Communications.
Thank you very much. I hope this will work this time, but let's see. It's off at the moment, so probably, yeah, now working. So yeah, sorry to interrupt your discussions, but I'm very glad to be here and to introduce this, let's say, next session with a small talk about how we support innovation and collaboration from Estonian government side. So my name is Mikk Vahtrus. I work at the Ministry of Economic Affairs and Communications. My background is actually in physics and material science, so I know a few things about DC, but yeah, for the last 6 years I've been working in the ministry in the various roles. At the moment, my job title is Research and Innovation Sector Manager, but from Monday I'm also the acting director of Department of Innovation and Technology. So to start off and to, let's say, pose a question, I have a slide that says Estonia, the best place for technology transfer and science to business collaboration. So, of course, this is probably not true, but it is something that we are aiming for, and why we are working at the ministry to support this, let's say, collaboration. And for the next few slides and 10 minutes, I will just briefly talk about what are the ingredients to achieve this, which are the strengths and weaknesses of Estonia, what are we doing to support it, and then I will conclude my talk. So again, I'm not an innovation expert, so to say, but again, a very, let's say, easy way to explain how to, let's say, support or what is needed for innovation to succeed and collaboration to succeed. You need different ingredients. So you need, of course, human resources, you need very talented people, you need academic know-how, you need business skills, you need entrepreneurial mindset. Of course, you need financial resources, so you need the public sector support, but you also need the private sector money. So you need the venture capital, you need the, let's say, so-called own money, or the money that has been accumulated in business or private sector over length of time. Of course, you need absorption capacity. So if you have this great knowledge, you have the money, then you really need those entities that bring innovation to the market. So you have your SMEs, large corporations. Now we talk about very much about deep tech startups, but also public entities, because again, one of the main clients may be public sector. And to bring this all together, you need intermediates. So you need the people who can translate this excellent science, technology to business and bring these actors together. So you have your universities, technology transfer offices, you have your science parks, innovation agencies, incubators and accelerators, and research and technology organization. And all this together creates the innovation ecosystem. So all these parts need to be there and they need to act together. So if we look at the, let's say, Estonian innovation ecosystem and what we see are our strengths and weaknesses, then of course we like to think that Estonians are very entrepreneurial people. So we have from the beginning of our independence, we have been very entrepreneurial. We have a very strong startup culture and background. We still like to think that we have a very good business-friendly environment, especially still we rank top among the top countries in our taxation of businesses. Of course, we have excellent research, again, ranking in different, let's say, scoreboards in the top. We have a national commitment to fund research and development of at 1% of GDP. Of course, thanks to our startup culture, we have quite good venture capital access and quite various programs that are being funded by public sector. On the downside, of course, the main, let's say, limit is our small population and our young country. So we have limited talent pool. We have really the lack of own money, or we have very few large companies that are R&D intensive and could, let's say, ignite these ecosystems that we need. One of the things is that we have quite limited collaboration between academia and businesses. So, and also I would say that business-to-business collaboration is also something that is lacking. And I think that's something in the nature of Estonians. So we don't like to talk to the other people and we don't like to talk to our neighbors very much. So this is something I hope that will change in the future. We start to collaborate more. Again, comparing to other countries like Nordic countries or Germany or any other, we don't have this established research and technology organization. So those who can really translate academic research to businesses. And of course, like many other European countries, we have a very small domestic market. So we always need to think globally if we start to innovate. So this is a very busy slide, and I will not talk about this slide in detail. So just try to draw a map of our ecosystem with all the actors, starting from the ministries to the universities, with private research institutions, innovation hubs. Just to highlight one thing, which I didn't include into these slides, but the main, let's say, funders are the Ministry of Economic Affairs and Ministry of Education and Research. And for us, we have a joint strategy. So we must work together and we have common, let's say, goals. And in this strategy, we also have focus areas. And one of the focus areas is smart energy solutions. So again, just to link this bit to this today's event, for us, it is very, let's say, one of the focus areas is how to innovate in the energy sector, how to bring new innovation to the market and also to the let's say, public sector. So now we'll talk about a few of the, let's say, support systems that we have in place. And I will start with the Ministry of Education and Research.
And here you can see how we try to, let's say, tackle some of the gaps we have. So we have from the Ministry of Education Research, mostly this technology transfer and innovation support schemes are funded from the European structural funds through different programs like Astra Plus, which supports the universities technology transfer offices, skill development, and also the proof of concept grants in the universities. Then we have thematical R&D programs, which are in these focus areas, which I mentioned before, the smart specialization fields, and these projects that are funded in this program should also align with the industry and public sector needs. So to, let's say, address the skills and talent part, we have sectoral mobility to encourage movement from the academic sector to the business sector to the public sector and back. So to get people moving, to get the collaboration between the sectors working. And of course, international cooperation, so participation in Horizon Europe, including different partnerships, teaming, and the European Research Council Seal of Excellence. From the Ministry of Economic Affairs and Communications, we have, let's say, mostly concentrated on applied research. So we have a applied research program supporting from TRL 3 to 7. And this really focuses on the business's needs. So the businesses or the companies are the applicants, and together with service providers, including universities, they can conduct these applied research projects. And we are in the middle of our evaluation at the moment of one of our application rounds, and actually we have quite few projects that are very much connected also to the electrical grid, to the optimization of this grid, allowing, let's say, to use it more efficiently. Again, coming from the fact that our grid is changing, there is so much more PV and other sources that are connected to this grid. We are establishing our applied research center in 5 focus areas. As I mentioned, deep tech is something that is very fashionable these days. So we have different kind of support for deep tech companies. So we are establishing a pilot program with science parks and universities to bring out new ideas, to bring new companies out of the universities and to provide them with all the knowledge they need. Also different accelerators and business development grants. From, let's say, a capital side of things, we have smart cap funds on green tech, defense, and also venture capital funds. And also the Ministry of Economic Affairs is responsible for the European Space Agency and CERN, and provides of funding for the main programs and optional programs in there. So to sum up, of course, innovation is driven by collaboration, and we have some, let's say, advantages that we can use here, but still there are some gaps we need to close, and that's the role of our work, to close these gaps, to understand these gaps, and to help, let's say, businesses to grow and innovation to flourish in Estonia. Thank you.
Thank you, Mick. So one question maybe from the audience. Yes.
Yeah, if no one has a question. You mentioned TRL levels 3 to 7 for the programs you fund. That is good. I'm just wondering, do you also support actual investments in real life installations that maybe need some initial nudging or support to overcome the higher initial cost?
Well, yeah, it's a difficult question because from the state aid perspective, it's for the state it is always much easier to fund this TRL 3 to 7 because there are many state aid exceptions. So for a higher, let's say TRL level, we can offer some loan guarantees or loan services, and also for bigger investments, there are some grants, but they are, let's say, the support side is quite small compared to the, let's say, applied research where you can fund up to 80%.
I'm not thinking about 80%, but like just kind of a little support for the, let's say, early adopters to the technology. Okay, thank you.
Okay, thank you, Mick. And like to all of our presenters, a small gift for you. Okay, a photo. Thank you again. Applause, please. Okay, we are moving to the next presentation, which will be made by Reigo Hauk. So he is a representative of Elering. For those who doesn't know, this is a state-owned company, basically an Estonian transmission system operator. So please.
Good afternoon. So my target for the next 12 to 15 minutes, actually I do have two targets. Firstly, keep you awake so you're not falling asleep during the next 15 minutes. And the second thing is to give the high voltage side kind of aspect to the show today. I have been involved with the energy business about 25 years, and the past 17 has been somehow related to the DC systems, and also for Elering. So what is Elering? Elering is the transmission system operator. We are dealing mainly with AC, substations, overhead lines, cables, even emergency reserve power plants, synchronous condensers, you name it. The DC came in to, and what we are actually doing is we are kind of keeping the economy alive. We are defining ourselves through that. So we are maintaining or providing the security of supply. And the DC came in actually already some time ago. In 2010, I think it was in 2008, we started to plan the S-Link 2. And at first it was different. It's the same, it's a different. And I just wanted to express it's through Ernst. He has made some marvelous kind of statements. So it's HVDC, it's not AC, guys. You need to remember that. It's totally different. And once, if you have already, I don't know, is there a pointer as well? If you have already fall in love with it, then then once HVDC, always HVDC. So it is what it is. The HVDC community is quite big. Actually, it's very small, to be completely honest with you. And all of the guys, they are freaks, as myself as well. But we have all the good and close cooperation, and there are a lot of connections all over the Europe, all over the world. What we are concentrating next 5 minutes is the interconnectors in between Estonia and Finland. It's 1,000 megawatt connection, but 1,000 megawatt, it's nothing for the Europe. It's relevant for us because today in the morning, the consumption in Estonia, it was 1,200 megawatt. Production 700 to 800 megawatts. So in principle, with those two interconnectors, we could, in average, cloudy autumn day provide the whole energy, either from Finland to Estonia or from Estonia to Finland. So that's where we are. And together with the Nord-Baltic connection, the half of the Baltic's energy could actually be provided through the HVDC connections. So that's kind of the background information. And we have two connections, quite the same, quite the similar. We have the both systems, the Baltic source converter, the Estlink 1, the second generation IGBT, ABB connection, symmetric monopole prototype, I would say. Started in 2003, commissioned 2006. It used to be quite caprice, but now it is working well. It's simple, it's complicated, but it's also simple. And on the other way, we have Estlink 2, even though constructed almost 10 years ago, used the older technology, the line commutative converter, the current source converter. And the reason for that was mainly because of the lower losses back then, and also the reliability. We tried to have the well-proven technology because we need the tractor who is doing the work. But nowadays, since the market has changed a lot, we need to the tractor needs to cook and bake and do everything, do the laundry as well. So everything needs to be included. And what is the main point of this HVDC stations actually is that to provide the support for the grid. Of course, it is meant for transmit the power, transmit the megawatts, but the real reason is, or the benefit for the grid and the reliability is the higher level control functions, the frequency control, the emergency power control, the POD, power oscillation damping, subsynchronous oscillation damping. These are the features what plays the role, plus the black start capability, which if something happens, such as in Iberia, this could actually, Estlink 1 type of the converter station can support us to survive, point one, and also the restore. Main things. And are they relevant? We can produce everything in the lower level, in the low voltage side. But there are sufficient amount of consumers, end consumers, who don't have such technologies available. So therefore, Ellering's kind of target is to guarantee that all the consumers are provided with a secure energy, and that's what we can see also from the graph. So in the lower here, there's years, and this is the utilization rates of the Estlink 1 and Estlink 2. So we can see that it has been increasing from 2017 onwards, increasing and increasing and increasing all the time, until we had the first cable failure and then the drop down. And this caused also quite a big bottleneck in between of the energy transfer. So based on that graph, I could say that it is relevant, it is needed, but it also includes several risks. So as we can see from the graph, so there are some more friendly and more unfriendly countries nearby. Everything can happen. And on those interconnectors, what we have had, from 2006 and 2014, we have totally more than 150 failures. Only 2 cable failures. Most of them are related to the converter stations. Most of them are related to some auxiliary systems. Fascinating faults, I would say. And it never gets bored with HVDC. I can guarantee that. So typically, the topmost issues, those are the kind of issues with the greatest kind of impact, but there are always minor details what will matter eventually. And what will come next? I don't know. Will it come or not? No one knows. So after the Estlink 2 was commissioned, almost instantly started to, do we need more? And first years, maybe it was not visible that we need more, but from 2017, if we saw the trend that utilization rates go up higher and higher and higher, then quite soon the issues with respect of the Estlink 3 started to on the table. So do we need it? When we need it? What is the rated capacity? So I need to say that those are the plans. I don't know. Is it a 320? Is it 500 maybe when we are approaching to the kind of tendering phase, maybe the 500 level is such that we can already trust that. We should avoid the mistakes what we have done with Estlink 2 to have a sexy, marvelous design. This Estlink 2 cable, integrated cable, 2-in-1, superb. It's a masterpiece, but awful to find the faults, awful to repair. Takes a lot of time. Why else we needed actually 7 months to repair this piece here and 6 months from the vessel. It is time and the money consuming. The cost of the 2 repairs only, it's not 100 million, but it is close to 100 million. And the original installation cost of Estlink 2 back in 2010 when we signed the agreement was 180 million. So half of the price is now paid through the repairs. But we will see what will happen. When the expected time, 2038, comes, then the middle-aged lady here, she will be 30 years old already. No one knows what is the expected lifetime of the IGBTs or BIGTs nowadays. So we will see. I think it will be the time of the interest. Anyhow, whenever the Estlink 3 comes, we will build all the needed higher level functionalities such that the Estlink 3 most probably will be similar to Estlink 1 with the voltage source converter technology. Is it the bipole or is it the monopole? Irrelevant now. The feasibility studies are ongoing, and if it's needed to be constructed, it will be constructed. Let's see how it goes. So I think I have consumed all my time. The only thing what I need to tell is that once HVDC, always HVDC, and I like what Mr. Told here earlier, that DC is fun. Yes, DC is fun, HVDC is fun, and in addition, the DC arc, the flame is brighter as well, so you need to remember that. Good. So that's thank you from my side.
Thank you, Reigo. So one question. Anyone?
Question from behind the curtains. I know the number, but I want others to know. What is the payback time of HVDC lines in Baltic Sea? People typically surprised by the number.
I don't know that, but it depends about the amount of anchors passing through, I would say.
But is it safe to say we are in 1 to 2 years range, using all the money earned from arbitrage of energy between countries?
Yeah, you're pushing that button. I cannot confirm. I would say that the payback time is so relative. It depends, I think, how Elering is actually operating the cables, the links. Typical people is a cable, is that we are kind of operating it on market pace, and we are not after it's not a commercial link. So what we are after is to kind of couple the markets in I don't know, here. So actually, no, I cannot say that. I think our target is to keep the cables up and running, even if it's kind of financially could it be kind of unbeneficial for Elering, but we are here for the society. And what I can say, I cannot give you the payback time, but I can say the number that the faults that we have had with the cables last year and this year, I think the kind of socio-economic benefit or socio-economic loss is more than 100 million euros. So the price that the Estonian citizens has paid more because of the Estlink 2 has been failed is more than 100 million euros. So therefore, it's quite complicated for me to say the feedback number. I can also say that whenever we have had Estlink 1 failure, for instance, even if the failure is 4 hours, we need to do the counter trade, and the counter trade can be also kind of the cost of the counter trade of the energy. It can also be several hundreds of thousands of euros, if not millions of euros. So I will not give the figure. If you're after the number, you will be disappointed today. Good. Thank you.
Thank you very much. So a souvenir. Thank you. Now we have a couple of more presentations now from the private sector companies. So the first will be Arsen Muradov for Bergman Technologies. So please.
Hello, everyone. First of all, I would like to thank everyone involved for arranging this beautiful DC workshop and a lovely lunch. I'm feeling slightly sleepy right now, but I'm sure I'll handle it. I'll try not to take all of my 15 minutes, and I won't go too much in detail. Okay, closer. And too much closer into a DC, but I will, with pleasure, explain and tell you more about Bergman Energy, what we do, and about our future plans. So Bergman Technologies is actually a mother company of Bergman Energy that is purely involved for the EV charging and BESS systems. We also have Bergman Engineering, actually called Krakow. The company was purchased several years ago that is actively working in developing various, let's say, solutions in the defense sector as one of the main sectors they're working with, also med and health and marine tech. Bergman Energy is responsible purely for the EV charging, and Bergman Mobility for the remote control, let's say, all these delivery robots that you probably see on outside for the technology that you use to control this equipment. So as you can see here in the picture, this is our product line, current product line that is already installed in Europe. On the left-hand side, you can see our DC-1 charger that is not on the market, unfortunately, yet, but it will be rolled out soon. That supports power from 30 to 400 kilowatt, fully air-cooled. Next to it, you see the BEX 150. So this is up to 150 kilowatt charger, also stationary DC charger that supports both CCS2 and potentially, if needed, which I doubt anytime soon, GBT. And our widely used and famous DC charger wall box 60 kilowatt that is actively used in Norway at the moment. And we also, of course, manufacture DC mobile chargers that are widely used in warehouses, repairing depots, and so on. What we are exploring right now, I cannot go into detail as a NASDAQ listed company, and I cannot tell you anything before it's actually listed in NASDAQ about us, but we are actively exploring partnership and operations in the Middle East. We've talked to be more specific in the GCC, and I'll come to it a little bit later. And obviously, this particular slide will show you that our equipment is designed for the all harsh environment, both heat resistant and cold. So what we do at the moment, we have our development laboratory, engineering laboratory here in Estonia that is also used for assembling our DC equipment. And we also have a big factory in partnership in Sweden, Norrtälje, where we manufacture our equipment for the Scandinavian region. At the moment, despite Bergman Energy on the market is only for a couple of years, we already reached very big milestones, and our equipment sold together with Daimler Mercedes trucks. And as I've mentioned, our main, let's say, market right now as I speak, unfortunately, it's not in Estonia, which we're working on fixing, but it's Norway and Sweden. And so as you can see, there is a lot of already, let's say, live installations. There is a pictures. Oh, how do you do this? Yeah, here. This is in our Swedish Norrtälje factory, where we're assembling our, let's say, most commonly sold charger right now is a DC 60 kilowatt, which goes both on the walls and it can be also on the standby. It's advertised widely in Norway as well. And as you can see, there is some Mercedes trucks with it. And this is on an exhibition where Daimler have introduced our equipment together with the trucks in Norway. So we are small. We are pretty fresh and new on the block, let's say. But despite that, we're doing, let's say, big steps, not fast, but slow, but still we are doing them. And we are looking, let's say, for the next 2 years would be very crucial 2 years for our company in terms of development and filling the EV infrastructure with our equipment. Also, obviously, we were thinking, and due to a lot of conversations with our existing clients, potential clients, we hear from everyone about, let's say, lack of grid power available for high power chargers. Some companies, for example, as assume a chain of petrol stations, everyone wants to have DC chargers at their charging points, but they don't have enough grid power. And for that, we started receiving a lot of requests for the battery storage provision together with our equipment. And for that, we have signed a partnership agreement with some European and Asian manufacturers. And we also provide right now not only DC charging systems, but also BESS systems. We even went a step further. Some companies that are in, let's say, in transition from diesel to the EV transportation, or companies, including mainly logistic companies, big logistic hubs that are planning to transit to electric, but we're not, let's say, they're afraid or don't understand or don't want to use their capex for the, let's say, transitioning to build charging hubs and so on. And for that, we even, let's say, made an extra step forward to make a, let's say, single window solution for our existing and the future clients, where we can, together with our partners, even finance their plans to go green, to go electric. And from the project value from 500 above, we can we can finance, cover the whole, let's say, transition from starting from the project design to installing equipment, maintenance, and so on. And in this case, client go from CapEx straight to OpEx, which I believe it's a, let's say, a very good option, and services that are not everyone, let's say, proposing right now. But as Mick rightly mentioned, I'm not sure if he's still here or not, in Estonia is famous for being innovate and doing good and extraordinary, let's say, initiatives, which we are right now obviously also providing to our clients. So I kind of, let's say, jumped ahead a little bit. This is what I also wanted to, well, I just covered for that particular slide. So we, Bergman Energy, strive to provide all-in-one services to clients, not just consultation, not just equipment, but financing, project design, installation, maintenance, and everything. We provide to a client everything what is needed. Also, what is good to know for everyone, our chargers, unlike some chargers that are right now facing the issues with new electric vehicles, we're using a very famous German charging controllers that are recognizing all trucks, buses, and vehicles, and there is never problems with the handshakes, which is very important. So our uptime right now is 100%. We had some initial issues with the settings and with the even with the casing. We had some issues at the beginning, but right now all the issues are fixed. And we have 100% uptime, and our clients are very happy with our kit. So, and obviously, as I've mentioned at the beginning of my speech, we're actively exploring business in the GCC, and we see Qatar as a future GCC hub for Bergman Energy, where we will manufacture and deliver our goods, our equipment to whole GCC region. Thank you. So I try to be kind of straight to the point. Thank you very much.
I'm asking, are you guys working on the battery chargers for different batteries apart from lithium ions, like sodium ion batteries, different kinds of batteries? Are you working on designing converters for them?
We don't design converters, but we work with the different power modules, if this is what you're asking. And we also, by the way, I forgot to mention, and I apologize for that, you reminded me, but we also now, as we have now in partnership with the best system providers, we also now rolled out DC chargers integrated into the best system that can be used as, let's say, emergency charging services for buses, cars stuck somewhere with an empty battery in urban areas or outside the cities and so on. So yeah, we're kind of, let's say, all-rounders.
Now, before we continue with our next presentation, I would like to maybe a little bit ask. So, you know, Estonia, despite being very small, we have quite a bit of actually unicorn startups. Who knows how many startups we have in Estonia? Okay, yeah, someone answered. It's 10, indeed. So I call to the stage, maybe 11th unicorn in the near future. So Max Van de Pol from Skeleton Technologies, please.
Thank you very much. Is there a clicker? Thank you. Okay. Good afternoon. And yeah, hopefully number 11. So I'll start with a number. Estonia last year, I think, reached a peak load of about 1.6 gigawatts. And Orego, just a moment ago, mentioned that this morning that load was around 1.2 gigawatts. The reason I bring this number up is to put a bit of scale to the size of what's coming down the line when we talk about data centers. Data centers at the moment are coming in at the scale in the next 4 or 5 years at about 1 to 5 gigawatts. So roughly the size of a small country like Estonia or a medium-sized city. And this isn't just once per year, but continuously, cyclically, at millisecond timescales. So no grid on the planet wants to know about what's about to deal with this. So big stuff coming down the line. So I think you can probably guess then what I'm getting at here is that the problem isn't going to be even the chips or the software, but rather the access to power. This is the constraint. And even the biggest players in the world, Satya Nadella from Microsoft and others, are talking about they've got the chips, they've got the racks, but what they need is the hot shells. And what they mean by this is simply data center buildings they can put their racks in that are ready to supply the power and energy needed to actually run AI training loads. And these loads we are starting to see are doubling on a yearly basis, annual basis. And in some cases, we've seen them double within a single year. So this is massive, massive growth. And so data centers at gigawatt scales, they're not theoretical, they're here. And we've got 5 gigawatt monsters coming down the line. And so the problem here is that the grids simply can't keep up. Western transmission and distribution and substation upgrades, they take about 5 to 10 years. And there's a lot of really tough cases in the Western world. For example, in the UK, they estimate they've got about 750 gigawatts of grid connection queues. And I saw that number could even reach 800, depending on where you look. So this means that if you want to connect to the grid right now, you may have to wait behind other businesses that have many, many gigawatts to connect before you do. And it doesn't matter how big you are. We can look at, I just saw literally yesterday, Microsoft are building an AI data center in the UK, and this will be built around 2027. But they won't get a connection to the grid until 2032. So if Microsoft can't do it, God help everyone else. You might have guessed that I'm from Ireland, and Ireland has been quite at the center of the data center space for a while now. And we've had laws in place to prevent you from building any more large-scale data centers because the grid simply can't handle it. A little over 20% of the Irish grid is covered by data centers. So the law is no more. Because even though it's a relatively wealthy country, it's civilized and modern, my parents often complain about 5 to 6 blackouts per year, not to mention the annual traditional Christmas blackout. So that law changed quite recently because AI is big and every country wants to be at the center of it. So Ireland changed the law and explained that you can build new data centers, you just can't connect them to our grid. You have to run on a microgrid, you have to do it yourself. And then there's the US, who always like to do things big. Their AI data center companies are simply bypassing the grid and utility companies entirely and building their own energy production, and most commonly with gas-fired power plants, which maybe take about 18 months, or wherever there is a nuclear power plant that's been sitting idle, they're building a data center next door and they're spinning that power plant up. In fact, I don't believe there are any idle nuclear power plants left in the US. So the result here is that AI infrastructure, it's scaling at software speeds, but the grid can only scale at kind of civic speeds. So worth spending a moment on the AC side of things. And here I think it says it all. These high power AI loads, they're extremely transient in the spikes, and the spikes can be 50, 80, 90, even 100% load swings from the base load to the peaks. And it's happening in the millisecond range and low milliseconds. So the traditional AC side, power electronics, the transformers, converters, the bus bars, the cables, they all add latency to the situation, and some smoothing, and unfortunately too slow for the transient AI loads that are coming through. And so we get this disturbance. When it arrives and it's aggregated, it's delayed, it requires a much larger solution outside in containerized solutions, and it's more disruptive. It's, as you can imagine, less efficient. So when these spikes come through and they're propagated and they start to reach the racks again, the power supply units, the voltage regulation modules, they start to try and protect themselves and the infrastructure that they are responsible for. And they start to throttle, they start to derate, and of course this slows down compute. And while this slowdown may only be about 3% over a year, when we talk about the scale of these data centers, the massive running costs, this 3% is massive in itself. And they're going after percents and less than percents anywhere they can in terms of efficiency. So I mentioned a moment ago how in the UK we have there's about 750 gigawatts of grid queue. And like the US, data center companies are building whatever they can instead of having to wait years to get connected. But what this looks like in reality, I've spoken to many data center builders in the past year, and when we ask them what do they need, they talk about maybe they need 100 megawatt grid connection, but they don't really need 100 megawatts. Rather, it's quite a bit less than that in terms of base load, and so we look to solve this. So we want to solve it at the DC side, closer to the source. Closer to the source, the better we can handle it. So we build these smaller, faster modules that can absorb and discharge in those loads in a much more efficient way, actually at the time scale of the AI power swings, which is in the single-digit microsecond range. So we go to the what's asked for versus what's needed. When they say they need 100 megawatts, like I mentioned, they really only need 60 to 70 megawatts to cover the base load, and they add on sometimes an additional 50% to cover the spikes that come through training. When speaking with the data center builders, are asked, but if we could shave those spikes, if we could absorb those with something at rack level, what would that really mean for the data center companies? And it means cutting 30 or 40 megawatts in a case like this could save them up to 3 years of waiting time before they get that connection. And I'll very much be trying to get in contact with Microsoft to help them with that UK case. There are other pains though, because when data centers that exist now today want to expand, they're of course limited. And the pain becomes even worse when we consider that in some regions, as the temperatures start to rise during the summer months, those extremely hot days, the cooling requirements go up. And where the grid connection was sufficient for the peaks that come down the line, as we raise that base load due to hotter and hotter days, those peaks start to exceed the limit and start to cause either fees or fines from the utility companies, or simply the TSOs and the utilities, the grid that backs off starts to throttle and then slows down the compute that's needed. So there's a few options for those data center companies that want to expand on the existing load that they have. One, they can wait for the grid to be upgraded. I think we know by now this can take many years. Another is that they can build their own power generation, these gas-fired power plants. But even that can take up to 18 months, and it's far better than waiting for the grid. But if they can shave the peaks themselves at rack level inside on the DC side, then they can expand their base load significantly, knowing that the peaks coming won't exceed their limits. So we get to what we do at Skeleton. Skeleton's had many years developing solutions, high power energy solutions for the grid. We have a large focus on things called e-statcoms, or enhanced static static compensators. These are the systems that start to stabilize renewable energy coming into the grid and are able to support the grid if there is a sudden peak in power or a drop from power generation. So we think of the Iberian blackout in Spain and Portugal a few, maybe 6 or 7 months ago. That was a massive marketing campaign for Skeleton, because what we offer is a solution to prevent things like that from happening. But what we see talking with the major integrators, with the TSOs across Europe, is they've got some pains now, and those pains are growing as the energy transition comes and we find more and more transport comes onto the electric side of things. But also, we then came across the AI data center challenge that's coming. And so we were in a very good position to start addressing that quite quickly. And so what we developed is what we call the graphene GPU. It's this blade here. So you can see there, it's 50 volt, 40 kilowatts, and it takes up 1 OU. This was designed against the OCP standard, which is the Open Compute Programmer project that was developed by Meta and shared and used across the hyperscalers. And now most AI data centers and data centers being built are built against the OCP standards. And so 1 OU is 1 open unit. This means if you imagine a rack that has the GPUs in it, it has the power supply unit, it has the battery backup unit, they're in 1 OU slits. And so the goal here is to take up as little extremely expensive real estate as possible. So we developed the 40 kilowatt solution. The best that we've seen in the market that competes with us is about 24 kilowatts. So it's about 60 or 70% more power in the same amount of space, which means when we look at a 75 kilowatt rack, we can cover it in 2 OU, where competitors are looking at 3 to 4 OU. And again, this is extremely valuable real estate in these racks. But we continue to develop. This is really the first of a product line aimed at solving the power needs of AI data centers. And so coming down the line, we have 400 volt architectures, 800 volt, and even 1500 volt. And we need to continue to develop and innovate to provide extremely high power solutions in extremely small packages. This is what Skeleton is best at. But what's also coming down the line is, while I mentioned 75 kilowatt racks, or what we talk about today, tomorrow it's 250 kilowatt racks. And there's talk now, you see examples of it, where they have megawatt racks. Right now, the mean data center size is roughly 19 megawatts, which has doubled in the last few years we're almost doubled from about 11 megawatts. But you go back 10 years and the average data center was around 1 megawatt. Now we've got racks at data center scales, and we've got data centers at city scales for what they truly need. So if I bring it all together, summarize it, like we see about over 20 1 to 5 gigawatt scale data centers coming down the line, according to a few sources, Thunderset Energy being one. And the existing grids simply cannot handle this. One great example of this was Elon Musk's XAI building Colossus in Memphis. Memphis said there's no way you're connecting that thing to our grid. And so they had to use a lot of batteries and mega packs and others to have a microgrid for something like this. It really does come down to DC side innovation. We need to solve the problem right as at the source of the power draw. So on the DC side, in the rack, as close as we can get to the GPU. And so the AI scale out, it needs DC innovation. It's not just about the chips, it's not just about the software. It's about the infrastructure, the energy infrastructure we need. And so I will leave it there and say Skeleton is doing its very best to enable AI to scale to what it needs to be and to be able to support the grids around the world to host gigawatt scale data centers. Thank you very much.
Thank you, Max. So yeah, we have one question.
Thank you very much for the presentation. I have the question that is the supercap producer support energy transition or not?
Is the supercapping used to support the
energy transition from DC? Are you happy with current AC, or you also want from the financial perspective and all in mind?
Well, I think maybe what I've been showing here is that we're actually on both sides of the fence. On the AC side at grid level, that we need support there for the grid as a whole to be able to support the energy transition, to be able to support AI data centers and other say manufacturing activities, maybe metal smelting like electric arc furnaces. I understand these days they need to call the TSO to let them know they're about to start some operations because there are massive power draws. So we can support those power draws at the electric arc furnace itself, protect the grid. But in examples like AI data centers, we can support at the DC side as well. So there's both sides where supercapacitors are a big benefit. Of course, I would say that. Selling them, but
yeah, I have one also small question from my side. So if someone wants to have an engineering sample or some sample of your product, is this possible at today, or is it still in the future?
Yeah, absolutely. So Skeleton's been around for about 15 years, but it's been the past 5 or 6 years where we've had mass production. If you're on LinkedIn and connected to anyone from Skeleton, you'll see over the last couple of days, we've just opened the largest supercapacitor factory in the world in Leipzig. That was a big milestone for us. But we've sold millions of cells to, I can't say who, but a major German automotive manufacturer for their active suspension. Our cells are in medical imaging devices that need extremely stable power all over the world, in wind turbine blades, in trucks, starting engines, and the largest truck manufacturer in the world in the US. And many, many more examples. We've been millions and millions of cells on the market.
Okay, thank you. One final question.
Absolutely.
You said something about 1 OU, the stack size.
That's right, yeah.
I had the question related to that. You mentioned that it was like 40, I forgot 40 kilowatt.
That's right, 40
stack,
kilowatt.
1 OU. You also said that it can be scaled to higher kilowatt level. Is it like same stack going to higher levels or multiple stacks?
So in terms of say covering higher levels like 75 kilowatt rack, do you mean?
No, I mean the example was 40 kilowatt. You said it can be scaled to 1 megawatt, let's say, for example.
Yeah.
But does that mean multiple stacks of?
Oh no.
Single stack.
No. So if we go up, say, a megawatt coverage, then it's more likely in a sidecar. So a cabinet on its own of just energy storage to cover a 1 megawatt rack. Does that answer your question?
Okay, so it is not about 1 OU scaling to higher kilowatts, for example.
Yeah, so where we are at with the 40 kilowatts, with our next generation of supercapacitors, we're likely able to almost double that within the same space. And this is very much what keeps us very interesting to those AI data centers that are looking to increase the power of their racks. We're also developing and innovating consistently to provide more power in the same amount of space. So maybe we'll be able to get within 1 OU 60, 70, 80 kilowatts. But if we want to cover 250 kilowatts or a megawatt, then 1 OU will simply not be enough. And we start to move to a thing called a sidecar, which is a separate cabinet.
Is there also a limit for the length of OU or? Is it a volume constraint or?
It's rather, so its depth or like height is the OU. The racks from memory, I can't remember how deep they are. I think they vary a little bit, but for the most part, there's relatively standard kind of a depth of the rack. So our unit is maybe about yay long. Yeah.
Okay, thanks.
Okay, thank you for answering the questions. And a souvenir.
Right, thank
to
you
the
very much.
speaker.
Thank you.
Okay, applause.
And now, yes, we are entering the last phase of the meeting today. And this will be all about Taltech. Since I remember Hartwig's presentation, what we need to do for DC, and Yannick was also mentioning, Yannick. So we need to showcase, we need to demonstrate. And basically, we see that Taltech is capable to demonstrate things quite soon. And so this session, the next session is all about how Taltech is going to demonstrate things. So we recently got some funding for some interesting projects just to demonstrate the advantages of DC, but all things will be physically implemented in Estonia. And most of the things will be done in Tallinn. So 4 presentations about 3 different topics, and let's start.
Okay, thank you. So I will take 2 presentation slots now. And yeah, as Dmitry mentioned, we talk about the project which have been started this year, basically at Tallinn University of Technology. So the first one is related to the street lighting. And basically, I will not repeat myself too much, but we know about traditional street lighting. It's supplied by the alternating current, and we know the wire sizes. We know that the LED actually is the way to go in the future, and most of the cities are now actively changing, if not changed completely, to LEDs. And these devices use direct current, unlike previous technologies, which were basically supplied by AC. And as a result, now we need to use the LED drivers, which are basically AC-DC converters, and it leads to some complicated systems. We also look a little bit in the future, where we want to integrate renewables into the street lighting and also possibly some extra services like EV charging. And basically, if you look at all of these technologies, you can see that they are all basically DC. So why should we use AC now in the DC light? Why not to use the DC lighting? And Lawrence already gave good examples of why it is beneficial. It can use less copper, less switching counters, better reliability, some additional functions like grid monitoring, and so on. So we decided to go the same way, basically to have something in Estonia also. And actually, the project we got is called Lightline, and this is all about implementation of the first DC public lighting in Estonia. So we have one location in Tallinn. It's where in the city center, Lembitu Park, close to Ministry of Foreign Affairs. And another city participating in the project is Jablonec nad Nisou from Czech Republic. Here is some information about this project. So basically, both of them are related to park zones. It was decided because cities were very cautious, like of building something that is not standardized in a normal way. There were a lot of questions regarding, let's say, the extra costs related to warranty and so on, and servicing. We need to collect a lot of signatures, so it was quite a bit of a headache, but luckily we have done it. So yeah, about the projects a little bit. So this is the Czech park area. It has been waiting for renovation so quite a long time, and basically this project is connected with the full reconstruction. So we received some knowledge from the Netherlands, who were the pioneers in this kind of installation. So we decided not to retrofit some existing AC infrastructure based on like old cables, but rather integrate the project into some new city, let's say, reconstruction plans. And we so far got some preliminary, let's say, project of the renovation. So there are now 3 feeders in the park. One of them is agreed to be run on the DC. We'll try to now make at least the other 2 to be built. Maybe they are still cautious, but we'll try to build as they do often in Delft, that they build the DC ready AC solution. So later we can maybe reconnect them to the DC once they have some, let's say, experience with operating of the DC line. And another one is related to Tallinn. So this Lembitu Park, which will now be in the near future, will be reconstructed. It will be, there is a reconstruction plan, and it will be named Ukrainian Garden, red lines. Yeah, this is the older project, and this is some, let's say, sketch. So there will be some installations related to the topic, and also now we will soon start negotiating how can we implement the lighting project in this park area. And basically the realization will be quite straightforward. So we are not inventing or like trying to implement a lot of things this time. So we will be installing a cabinet with the commercial rectifier, some solid state circuit breaker, and also let's say the DC compatible LED driver. And so far, as we have the, let's say, agreement, we will install 30 posts in Tallinn and around 12 posts initially in Jablonec. But if we look a little bit to the future, how we see, let's say, how we envision the street lighting in the future, what can be there. So the project will be quite simple, but after, let's say, some period, we would like to obviously put there some, let's say, extra hardware, for example, electric vehicle charging hardware. We can install renewables there. We can put stationary battery there. Also provide some, let's say, or expand this, let's say, IT system with more functionality, ancillary services. And basically, these chargers can be used not only for just charging of the vehicles, but they can provide vehicle-to-grid functionality. And this opens up a lot of, let's say, novel services, from security ones or like emergency situations to some maybe commercial ones like vehicle-to-vehicle charging. And actually, this concludes this part of the presentation, and I will move to the next one.
Ask people maybe some questions so far. Since I have one, you were scrolling your slides very fast, but can you scroll it a little bit back? More.
Okay.
More. One more. And once again. And this is the slide. Guys, remember the year 2027. So most likely we'll invite all of you, and Andrei will cut this like a red line, right? So yes. So 27 is the magic date for all of us to remember. So it will be the most likely the first open DC space there, right?
Yeah, we don't know the exact months now. It's too early, but we hope that, yeah, this year is actually, we plan to make it run. Okay, any more questions? Okay, you will have another chance. So my Next presentation is like a continuation of the previous ones. So we from the public lighting to, let's say, V2G charging, which was mentioned briefly already. So we all know that the number of EV is growing rapidly. There is a big push in globally to let's say, transition to the electric transportation, both in the private sector, but also in the on the, let's say, city transportation level. There are several directives related to that. And in Estonia, the situation is, say, like everywhere in Europe. The let's say the EV sales in Estonia, they are not like linearly growing, but still the number of EVs on the streets is rising. And if we go to the problem of charging, we had a few presentations already related to fast chargers. So what we usually see is like this end device, which you actually, where the cable is, which you plug into your vehicle. But in reality, there is also some, let's say, additional infrastructure there, some, let's say, substation and some power electronics. This equipment actually takes quite a bit of space, which can be problematic in certain environment, in the city environment. So there is limited amount of space in many locations where you can actually install this, and also limited amount of power where you can install this fast charging station. So they are a good solution. They have their own problems, like the cost, at least in Estonia, for charging from this kind of systems is relatively high, but also they are not really scalable. And for example, if we go to the, let's say, AC charging, that in this case you need let's say, to use the onboard charger, which is usually limited in power. Some models have a bit higher power level, but still there is not a, let's say, global push towards increasing the amount of power from the onboard charger. And this makes us to, let's say, think a little bit, rethink how we can, let's say, solve this issue of limited charging spots, particularly in Estonia. And we considered the concept of opportunity charging. And yeah, here we talk about DC, and you hear the word opportunity. And maybe you consider, okay, maybe this has to do with this handsome gentleman. In fact, actually, it is, because we kind of think in the same direction. So if we go to the standard electric vehicle refueling, we are used to refuel it very, let's say, seldom. Usually we go full tank. It takes about like a couple of minutes, and then we can drive for, I can drive a week for or more even on the full tank. For, let's say, modern electric vehicles, we kind of maybe want to use the same approach, especially if you use fast charging. You want to fast. Obviously, it will take a little bit longer time, but then drive. And basically, since the distance traveled during the daytime on average is not that high, and we can, instead of using the previous concept of charging, we can use opportunity charging. So basically, if we install a lot of smaller, lower power chargers, which and we can then install a lot of them in many locations. We don't have these constraints of the DC fast chargers, so we can basically top up our vehicle when we park somewhere close to the, let's say, supermarket or just in the city center. And in many cases, this opportunity charger can provide 10 to 20 kilowatts of power, for example, and it will be still a higher speed of charging than in the most cases you can achieve with the onboard charger. And basically, this opportunity charging can be easily applied to the street light infrastructure, namely because in the daytime, this infrastructure infrastructure is just standing with no real use, so you can utilize it during the daytime. It has, let's say, the cables are unloaded completely, and currently it can be used with the AC and using the existing cable. But if we move to the, let's say, DC charger and DC street lighting, we can achieve much more, like I showed on the last slide of the previous presentation. So we can have vehicle-to-grid functions easily implemented. We can have these, let's say, functions as vehicle-to-vehicle charging. And also we can simplify all of our equipment, basically, which is connected to this street lighting. Also, this can be obviously extended to some, let's say, parking lots and so on, and integrate energy storage. So with our technology, our goal was to make this solution universal. So basically, we have now different types of electric vehicles on the streets, ranging from this plug-in hybrid with relatively low voltage batteries to some performance models with 800 volt nominal batteries. In the DC area, at least in the current OS, we have different voltage standards, or like different voltage levels. Most projects currently implemented in Netherlands, they are using bipolar 300 plus minus 350 volt. The project we will first, let's say, pilot here in Tallinn, we will not go that way. We will just use 350 volts unipolar because we don't, there is no need basically to use it in this relatively small project. But there is also 700 volt unipolar. And basically, from the power electronics point of view, this is a little bit of a challenge, how to design such a converter which can provide all of this, basically, a wide range output voltage and also allow different types of grid to be used, because we still don't really know which grids are going to be, let's say, the most widespread. Is it 700 volts or bipolar or just 350 will be also popular. So technology-wise, I will not go too deeply into power electronics, but we decided to go with this kind of a concept where we use a reconfigurable input stage, which have like two cells basically, and it can be connected in series to have this bipolar connection. It can be connected in series for the 700 volt and then in parallel to have 350 volts. So the topology is here. Basically, we have two half bridges on the, let's say, DC grid side and the full bridge. At the output side, it used topology morphing control to switch between full bridge and half bridge. And the basic operation, like basic topology behind this solution, is based on the series resonant converter. So far, we have made a laboratory prototype and tested it in various conditions. And basically, we tried, one PhD student is actively working on this now. So we try to implement different functions there, including droop control. And also we consider that this can actually do some functions in the bipolar grid, like the balancing function. We will take a look at that as well. And to conclude, we have a growing need in the solution which can be applied in the for the electric vehicle charging, and which does not have this constraint of the fast chargers. And we also want to look a bit in the future, so to have all of this vehicle to X functions included. And so far we have plans to test this solution next year in near our, let's say, playground, the DC Innovation Hub. We have one project. Today, this Astra Plus funding was mentioned. So this is actually the project from Astra Plus. We have some budget there, and yeah, the plan is to implement it next year, at least to do some first testing. We have already this DC light poles installed. So one of them will feature this charger. Thank you.
Yes, we have a plan to showcase it next time at next year's seminar. So far, we are progressing well. Yes, I'm asking our PhD student. Yeah, he is. Yes, everything good. So thanks, Andrei. And the second Andrei. So the second Andrei is coming to tell you something about Taltech DC Innovation Hub. So what you have there in Netherlands is very nice, but I guess we have been before you a little bit, half a year before. But you have much more powerful. But in our case, we have more power electronics inside, since we're a power electronics group. So Andrei briefly shows you what is inside. And for those who are willing to visit, many of you were there. But it's something new coming all the time. For instance, the lighting pole 350 VDC, street lighting test setup is there. But Andrei will explain.
Yeah, Dmitry, don't sell all the secrets at the first try.
I'm creating a spoiler.
So yeah, so the idea of this presentation is to present how this facility that we have here have been developed and what are our plans in the future, because we put it in stage. Every year we put a new stage, we increase and improve. So what we call it, it's a Taltech Residential DC Innovation Hub. And you see, this is a photo from one of our events with our, again, uniquely designed T-shirts. Is our own logo. By the way, logo is protected in European Union as a trademark, so you cannot use it unless you ask us. So, and we call it the first DC Experience Center in Northern Europe, because actually we start doing it earlier than DC Systems. So, so this is how it looks. It's thermally insulated, fully heated, operational throughout the year facility. Important thing that this, when we started establishing this already with a company, I will tell a story. We already been in touch with Schneider and Harry and so on. That's why Taltech have become the very first academic member of Current OS Foundation. I would say this thanks to this activity that was ongoing. The main point of this is test, demonstrate and validate different DC technologies for the DC buildings for the future. And you can also call it living lab, because it's not empty. Most of the time there is at least one or two or sometimes even 3 persons working there. For example, this summer our main research lab was closed for cleaning, so guys were fighting who can do research there, because at least they have access to some oscilloscopes and power supplies. Also we collect some data sets we generate, and this is a part of the big initiative. We called it I3DC initiative, as Dmitry explained, and we have a lot of supporters, and you can recognize some companies that are present here and also some Estonian companies that are not here right now, but supported us. So the main point of this that the structure, or at least the vision that we are slowly developing, but is that we have some embedded solar, and we have like different solar solutions. We have rooftop, north and south facing. We also have a solar facade, because you know in December, even if you have a sun, it will not help you, because our sun inclination to horizon can go as low as 9-10 degrees in December. So, but solar facade is excellent, because it's basically almost an ideal angle for solar facade. So this is something that works really well for us. We have indoor and outdoor lighting working on DC. We have a heat pump from Panasonic working on DC. We have some appliances that we already started developing with our students. We are running a DC club for bachelor and master students. When there are projects related to that, I think that this idea was inspired. But Dmitry will tell about that in more detail. Also, all small appliances are powered from USB PD, because this is the first real universal, ubiquitously used DC standard around the world. And of course, I will tell a little bit more about this development. Battery, second life battery we are working on, and Andrei just talked about this. This is like in plan to actually connect it to our grid. So each technology that we are developing has different names. For example, Merge is a smart energy gateway, or FlexiVerter is a flexible converter, and so on. If you want to know more, you know where to find us and contact. So as I told, thermally insulated, operational throughout the year. You can see here, for example, Sayed. This was the guy. Sayed, could you stand up? This will be the guy who can pick up everybody willing to take a look at DC Hub after this event finishes. It's just nearby. We didn't bring big crowd because there are some construction works going on site, but those who are willing to see can still go and see. So battery storage, this is more or less I told you about. Moreover, we have our system on the web by this QR code. So what we do there, as I told, we develop, we verify, and we demonstrate. But it doesn't mean it's only ours. We also demonstrate some devices from DC systems. And we are open to any company to bring in their device on site. Maybe Lawrence, who is promising for the last 5 years to bring his DC breaker. Just an example. But these are, for example, some devices that are being tested recently in our lab, some battery converter, breaker. This is grid interface, interlinking converter you can call. So everything is being piloted and we try to run them throughout the months and hopefully years to actually see how the converters operate and what is the performance in realistic operating conditions. This is something what I told you. If you go to dcnohub.com, you can see all our statistics in electricity and everything, good or bad. It is what it is. As I told, it's a living lab. Sometimes you can open it and you see that our DC hub is down because we're doing some maintenance or repairs. But it is in real time as well as the historical data as well as there. You can, for example, see different energy generation, consumption, and so on. How it started? So Andre, maybe you can wave to everyone. Andre used to be a CEO of startup Ubix Solutions. So it started as a part of a project with Ubix Solutions, where we have been in touch with DC systems, I believe maybe even Femtogrid at that time, when we had the chance to meet Harry for the first time. So this was installed next to it's in one of the marinas. This is actually, Harry, where you can park your yacht when next time you're coming by yacht. You see, this is a standing stand. Yeah, so it was about 10 kilometers from here, but this is what been installed, and most of the employees here have been us or our PhD students at the time collaborating with the company. And this was a very innovative project, collaboration with Estonian companies, for example, like Solar Facade. We have companies doing that who helped us to implement that at the time. And this is how I3DC initiative come to life, because this was the first spark was to start actually speaking about that between Taltech and Ubix Solutions at that time. And then by 2023, it was a time to move away from that area and to bring actually this DC hub to our facility. And this is very close, literally less than 100 meters from me, maybe 150 right now. So we need to put a fundament, and you see there are some guys who are still here, I think, with us, at least Tunnel. Most of our guys left the group because, you know, university is very dynamic environment. The students come and students go. But yeah, so we basically relocated it, improved, and start developing it next and next and next step. For example, one thing you would pay attention to, door was red and now is green. So an improvement, because we need to follow our corporate internal design. This gave us a chance to establish these different events. So there are like workshops like this, but also typically somewhere in spring, May or June, we are doing another type of event, kind of like an open doors, and you can see photos here. This is how we raise awareness, and this unique facility allow us to actually bring people and show, okay, you shouldn't be afraid of DC, and you should be aware of DC, because it's going to change your life one step at a time. And you see, so this was, for example, from Current OS Foundation assembly in Tallinn this June. So we had like, well, I don't know, maybe 80, 90 people on site looking at it. So here are only supporters have been allowed to go to this photo from different companies that donated different things to us. Moreover, I'm proud to share that our university is running kind of the Best Green Development Award, and we got a very nice award from university that commemorated this development. But I would say this award was given for phase 1. Right now we are in phase 2, and 2026 will be phase 3 of development. So what was the phase 2? You can see that there is like a DC connected PV shed, photovoltaic shed from one Estonian company using developing and building integrated PV. Also, we have established collaboration with Estonian heat recovery ventilation company, iRobot. So this is from Solarstone, from iRobot. We signed an MOU with Daikin, so we are going to develop in the foreseeable future not DC connectable, but actually DC compatible heat pumps. This is our inspiration together with Daikin, and we are working on their Altera 4 newest version of heat pumps. Tridonic is also a partner nowadays who is developing probably the biggest LED company of Europe, who actually develop things in Europe. So, and Kafatech is another partner from on a Miltech side, because military is DC for many years. Just people are not allowed to speak about that much. So everything what we try to do is to develop droop control, and in the future we are looking into scale up possibility, and this is what next presentation from Dmitry will be. Plants. Again, this is something what Andrei have been talking about, that we want to go to concept of energy neutral parking, and that's why we are developing this V2G chargers, because bidirectional charging is actually possible only through the DC port of your electric vehicle. Onboard charger allow you to charge but doesn't give you any other opportunities. And we are looking into organizing the very next DC Experience Day, probably beginning of June 2026. So mark your calendar. If you want to come, there's going to be more and better. And we will start showcasing more new technologies. For example, here, we just installed like several days ago, Second Life battery, which is a Nissan Leaf 9 or 10 years old battery that we just bought from a private person, because it appears it's not easy to buy a battery from electric vehicle in Estonia. But if you are innovative, you can. And also the DC hub, the solar shed itself is also ready. There is a converter here. It is connected to our DC grid. So we have some piping done through the ground on the street. So, and we have also street lighting. So there are technologies that we are developing now. So Andrei was speaking about UbiCharge technology more specifically, and the technology of Second Life battery, that we are developing with our master and PhD students and bachelor students. It's called Second Spark. So we want to give a second spark to Second Life batteries, hopefully without real sparks. And of course, our merge technology for interlinking converter. And Tridonic is one of the partners that we are looking into developing new solutions because you see we are going to really scale up LED lighting from DC, and this is actually probably the most common application, because any one of us nowadays have a LED lamp at home. If you don't, I don't know, you're doing something wrong, I guess. So as Dmitry mentioned, one thing to remind you that DC is not a district Columbia direct current, and there is an email of our initiative, so all of you are invited to collaborate if you are not yet.
Yes,
Thank
we
you.
would like to invite Ambibox, to join us, our testing platform. Thank you. So time for questions. So we are exactly at 3 p.m., but I will be there on stage for another 60 minutes. But anyway, so far Q&A session. So who is willing to ask Andrei, or who is willing to visit the DC container today?
So who want to visit? Let's start from that. Could you raise your hand? So after we finish the panel, you need to locate that gentleman. So Syed, please stand up again. He's our DC hub master. Yeah. So he will show you everything around. So Dmitry, let me run your presentation.
Yeah, but mine will be the last one. What we told already.
Last but not least.
But now it's the dreams become reality, right? Since what is good with all these nice partners, we are together for the last 3 years. And for this year, for the first time, I applied for the Estonian project, Estonian Team Ground. It was quite a bit of money. I mean, it's €1.5 million to develop the technologies which can save Estonian economy. And we decided to go for DC, and we decided to demonstrate that DC could be very nicely used in residential buildings. So what Harry is doing, and he was showing, he is building his house. But what I will be doing in my project, together with all my friends and supporters, since all of them have been supporting me. And yesterday we celebrated our win, right? So it was a promise, but now we have to deliver. And we are trying to deliver the new export item for Estonian economy. Basically, it's a prefab DC house, and I will show you what it basically means. So it's an Estonian Science Agency project. If you want to know the name, it's a PRG 3054, goes live next year. Quite ambitious project, very industrial. But the main motivation is that you want to, this or not, from 2030, you have no literally chance everywhere in Europe to build a house running on a gas. So that's already European directive. No other way around. All buildings, private buildings, will most likely run on electricity. So we will be entering an era of full or all electric lifestyle. This is what we have today. If we talk today with the AC system running of all electric lifestyle, meaning that there are no gas for cooking or no gas for heating the space, that's all on the electricity is the way we do it now. And I guess many of you were showing this diagram, right? And Kai was also showing another interpretation of it. But what is here to learn, this all red is bad. All green is good. That's why we decided to select the green color for our initiative. So all DC is green, is good. So the green color. AC is the rectification or inverting, right? So basically all DC things, we are using most of them today in our lives. Most of them are DC, 95% at least, even maybe 98, but all connected through the AC grid. There's rectification everywhere. So if you see some panels on the rooftop, you cannot consume your personal renewable energy. So that's a lot of complications. So you can connect single-phase device and three-phase system. Most houses running on three-phase system, and you have to think before you install your system on which phase you have to connect a single phase, for instance, charger for the hybrid vehicle. There are a lot of troubles around AC. How we see it in the future, the real nearly or zero emission building should run on DC. I mean, if we start building, I'm talking about new buildings. It's not about the renovation of the existing ones, but those new which are coming, they must run on the new technology. This is the good place to DC to come to the stage. Actually, the same picture, the same appliances, the same everything, but just the rectification is happening on a single point at the place when the AC is entering your house. And everything is inside is DC, but actually exactly the same as we use it today. Just avoiding rectification at every single point. A lot of advantages, I will not be repeating them. And this was the promise. But yeah, that's another aspect. Today, you was looking for the charger, and it was very easy to figure out, right? I mean, you need a USB Type-C, that's the charger for everything, right? And many of the appliances we are using today will most likely run on the USB Type-C. The power is rising, and the expected power limit is 240 watts. It's quite enough to charge pretty everything. If you need, you can parallel things to get more power, but anyway, so USB Type-C will be the main power delivery port for the low voltage appliance. If you want me to read the numbers, but I guess, Hartwig, I was copy-pasting from the document. You see the EU Strategic Energy Technology Plan, what you and Harry have been creating for all of us. So you can find it in the internet. I mean, all these numbers, I guess Vicky was asking me, Dmitry, where did you take all these numbers? So it was Virginia, I think. Yeah, I took them now from your document. By the way, everything is public. So you can save copper, you can save energy, you can save literally everything. That's the way to manage your V2G system. So that's all the advantages of DC. Read what Hartwig did, right? You can, it's a public document, by the way. No, but I mean, still, since you are today with us, it's much easier to reference you. People can ask you if they want. Anyway, so this is, if today, I mean, the building, what we run on AC, we call it zero emission building, is everything fine, and it's an A class. If we keep the same, everything, but just switching to DC, which gives us a chance to save the energy, we can intentionally go A+. And this is the motivation for the project, to demonstrate that's possible. And why I decided to go this way, not about charging, not about aircrafts, about buildings. In Estonia, one of the most important export items of Estonia today are the prefab buildings. You know what is prefab building, right? It's very easy going thing, so you can order this house from the catalog. Estonia is, I guess, leading the European market in this technology, very energy saving, very nice, everything, I mean, just was fine-tuned for the last 10, 15 years. Prefab is literally, could be a big building, could be a school even, or some public office, whatever, but could be a very small, tiny house. So I remember some German guys told me, we call it dacha in German. I don't know, it was Eastern Germany. But anyway, it was a small, tiny house, and the company producing these nice things is Estonian company Green Cube. And basically what we decided just to demonstrate that A+ building running on DC is possible, and basically it's our target and motivation for the next year. So I cannot promise you the showcasing by the next or in 2 years. The date for the showcasing is 2030, but the realistic time when we will start operating this building is 2028. This is the prefab. So everything is assembled in the factory, even the kitchenette. So everything you can see inside, that's a normal operational building with the roof, toilets, kitchenette, everything. I was selecting with these guys this room plan. It's a bedroom, you see a toilet, even a sauna, but sauna will definitely run, we will burn some logs, right? It's not an electrical heater. Since it's fossil fuels, right? This is also the open space. You can cook, but everything what we are using, except for the sauna and even this, it's a kind of a fireplace here. They will be running on the logs. All others will be running on electricity. Everything you can see in this shape, it comes out of the factory. So you just sign a contract, and this building in one piece comes to the place where install it, and it's operational one day. So that's the meaning of mobile or prefab modular house. And this is the way they build it. I was visiting, the name of the company is the Green Cube. It's a company specifically oriented on the small buildings up to 35, 50 square meters. It could be a single floor or 2-floor building. But anyway, this is the way to build it. And actually, it's a bunch of partners. And luckily, all of you sitting here supporting me will be participating as an advisor or as a component supplier. Daikin company, Andrei was mentioning before, we have an MOU with them. So the Daikin Alterma 4 will be redesigned to be droop control DC load. Current OS definitely will be used as the reference, as the operational system. There are no other choice for us. ODCA will be a supervisor. So yeah, I would like to have you on board to see how we do things. DC opportunities, we have to learn a lot from you and many, many others. And this is the way they transport these buildings, basically. They're using trucks and cranes, so they're just coming to your place and they install it within a day. We see it as one of the potential export items. And what Andrei was showing you before, it was a kind of a gym for me. You know, gym, you train your body, your muscles. What we do, we're testing these technologies to a nice level of TRL 5. And these technologies, most of them will be used in our project. Today, we have many of them to cover all our needs. And also the students, so students are those who are dealing with the DC appliances. I know Lawrence did something when he was a PhD student, just after it about, right? But anyway, so we have to put something, to bring something to the kitchen, right? And for instance, last year, our students, it's the name of this initiative, what we launched this year, is the Student DC Club, where the bachelor or master students just do some nice fancy projects. And for instance, this year we already delivered a DC kettle, for instance. I am not sure it's about droop control, but I mean, we expect it will be, right? Since you can have your droop control kettle. USB, sorry. So, oops, I went in the wrong direction. Microwave oven, droop control, LED drivers, and second life battery energy storage. They are the plan for this year. And in June, when will be the DC Awareness Day of Taltech, most likely we'll present all these new things. But those things will go to the kitchen of a new building just to demonstrate everything. So everything made in Estonia, that's the main point there. And also you see, you remember this gentleman, we are granting them diplomas and giving some money as well, right? I mean, so we select the best of the best students who are willing to contribute to the DC future, and they are developing things with us. And this is for the future. And I guess, Harry, you know, I see the neighborhoods, what you was mentioning before, as a very nice business model, by the way. So you can start earning money. Having a single DC house is good enough for the energy performance and satisfaction of the user. But to create some nice cash flow, I guess we have to go to the neighborhood level. And together with Sunly is an Estonian company, we decided to take a look on the business models. What can we get out of the DC communities? Basically, it will be a neighborhood. It will be, a village or a street with the building located nearby. So they are the plans. for the next 5 years, a lot of work to be done. I guess we'll work and communicate quite a lot. And thanks for supporting us. And we promise you, Taltech will deliver this technology by the deadline. Let's DCify the world together. You see, Andriy is there on the picture. Why I put him? Since Andriy will be organizing a panel discussion, right?
Yes.
Just after the coffee break. Thank you.
So thank you everyone for staying with us. I know it's getting late and late, more and more late. So our theme of the panel is that challenges ahead of the DC transition: business, social, and education. So I would like to again remind you who are our panelists today. You have seen all of them already speaking here or there. So Lawrence McKay is, I would say, the guy who actually established topic of DC in TU Delft, despite other beliefs, and who is an owner and founder of company DC Systems. And we have a Yannick Neyret. Sorry, DC Opportunities, my bad. Yeah, too much DC in Netherlands. Yannick Neyret, who is, for how many years are you with Schneider? 29? 37. So I was a little 8 years old. And right now he's the president of Current OS Foundation. Also we have Hartwig Stamberger, who is with Eaton. You haven't been with Eaton at the beginning. Your company was acquired by Eaton. So, but you are for probably also 30 plus years, I would guess. Yeah, within the family. Yeah, and also he is chairman and president of Open DC Alliance, and of course Harry Stockman. Let's call him a DC influencer, and also a founder of DC Systems, one of the authors of first Dutch national DC standards, etc. So I would like to start from a short, like a flash question. So each of you reply within 1 to 2 minutes. From your perspective, what is the single biggest barriers that keep DC in buildings, industry, and communities from moving from pilots to mainstream deployments in the next 5 to 10 years? So whoever want to start?
I would start with, we need pilots. To move from pilots to mainstream, we need pilots, and we don't have enough yet. Really not enough. It's not about 3 factories in Germany or 2 lighting system in the Netherlands that we have enough. We need much more. We need a data center. We need a commercial building. We need an industrial installation in Estonia and in Latvia and in Poland, everywhere. Otherwise, people don't believe.
Yeah, and oh, sorry, maybe. Okay. And what is super important, I think, is because the whole ecosystem need to be aligned on that one, and that's why you need more and more pilots. But what is super important is that we learn how to communicate the value proposition of DC, because I think that is one of the biggest, because most people don't understand electricity, and if you talk about all these technical numbers, then people look a little bit water burning, because they say literally with streetlights we have the same discussion. The streetlights was using very inefficient lamps. They moved to LED. It was huge efficient. So there was already a reduction of 80% of energy because of moving to LED. And now we talk about, we can save 4% more if you go to DC. And then people say, yeah, okay, but we make such a huge step. It's not interesting anymore. But that is what I mean. It is selling the value proposition in a proper way.
Yeah, and maybe let me continue with that one. I think really one of the really big challenges with DC that we have a lot of different benefits, and that's the problem. So there's not just 3 benefits or something like that, but there's a lot of different ones: efficiency, less materials, lifetime, all kind of different things. The challenge in most cases is that each of them alone can be quite little, right? So for example, efficiency. Yes, maybe some years ago we could save 30% losses or stuff like that. Power electronics get better and better, and maybe now you have either 99% efficient or 99.5% efficient converter. Let's say if you go from AC to DC, if you really pay a lot of money and do it at higher power levels. So if you start, oh yeah, nice, more efficient, but then you look at that, it's not good enough. But there's 10 other reasons as well, and you need to basically take all of them together, and then the challenge is also that per case it's very different how much benefits you get. So for example, the public lighting stuff, the copper savings, 75%. quickly as a reminder, that's just for these very long cables. Normally, it's maybe 50% or a third or stuff like that, right? But sometimes it's really a big change, and they change depending on what you do. And I think that's a big challenge to explain that. And I think normally marketing people say you should only mention like 3 benefits. And the challenge is for us, I think, is that usually 3 is not good enough for DC, but you need to take more than 3 to really make it work.
The barrier, or I'd rather like to call it the gap, I think in my view, for adoption of DC microgrids is closing. There are more and more installations out there already. I agree we need more of them, Yannick, so I pick up what you mentioned. But there are so many DC microgrid installations out there. Look at each PV field, which with a battery connected, that is a small microgrid. There's devices available, the EV charging, Kai, industrial applications, what I mentioned with Mercedes-Benz saying we'll roll that out worldwide. It's on the accelerating curve. Andrei.
Yeah, thank you very much. So I would like to move forward to a business perspective. And I would start from Harry, because you develop your own business and now you're helping others to develop their businesses in DC. So you often say that DC shouldn't be considered just as from component level, but it should be looked upon from a systematic point of view, how system changes. So the question is, when you talk to technology companies, district system operators or installers, what is the most convincing value proposition for DCs today? Is it OPEX, CAPEX, flexibility, efficiency, resilience? What do they still consider too risky?
Okay, I will try to answer it short. No way. Now, first of all, you have to understand, we have product companies, we have a system, and the system is providing business for product companies. So everybody is focusing inside the box. Everybody's making box to connect to the system. So this very in-box approach. And technically, when you talk about systems, you're outside the box. So you have to think outside the box. And this is very difficult because if you're a vacuum cleaner manufacturer, how to think outside the box if you're making vacuum cleaners? Because that is your core business. And the funny thing is, I can make a small example for cooker, for example. For cooker, they have the same issue. They're making water boilers. It's a very simple thing. So what is the business case for them to think about systems? But when you learn, I could convince them, because I said, guys, what you're making is a battery. You don't make a water cooker, you make a battery. If you're looking to the system perspective, and can you make with your cooker, if you can manage in the proper way the power intake, and you look to the system, what you can do to think outside the box and how you can solve it inside the box, then you create value. And then they say a little bit what the point here. This is very interesting because we never thought about that point that our thing could be in battery. And the same is for a kitchen appliance. That's very interesting because if I talk to Miller, for example, and the CTO literally say, Harry, what is for us the business case? We just make equipment, and if you quote to DC, it will be more expensive. I say, guys, you don't understand. Because the point is, if you look what your equipment is doing to the system, and if you look to a household, I can tell you mostly the 3 times 25 amp is needed for the kitchen. And if you have a guest house and you need to go to electric cooking, you need to do a big renovation in the meter enclosure. And I can tell you the electrician and the cabling for the kitchen appliances far, far, far more expensive than the kitchen appliance itself. So if you move to DC and you can fix with understanding what is your impact on the system, you can fix that in your equipment. Okay, you can charge double the price for your cooker, but for the end of the day, for the user, it's much cheaper. And that is the value proposition you have to bring. So maybe that's short enough.
Thank you. It's excellent. So I will forward my next question to Hartwig, since you have been appointed by Dmitry as a set plan representative, so there is nothing to do now about that. So, LVDC group set plan document specifically mentions that DC technology is largely ready, but standardization, protection, and regulations are lagging. So from your point of view, either from Eaton or ODCA side, what is the missing standard or regulation that are most directly blocking commercial LVDC? And if you could fast track one standard, which one would that be?
Yeah, thank you. First, a disclaimer, Eaton is a very large company, and I don't claim to be speaking on behalf of Eaton. I'm an educated voice from within Eaton, but I can speak for the Open DC Alliance. One thing, standards are describing the state of the technology. They are no laws. They don't forbid you to do things. They just describe what has been achieved. So nothing right now prevents the use or the installation of DC microgrids. That's important to remember. The one standard that I would address is the fundamentals of electrical installation in the IEC 60364 that describes the fundamentals of electrical installation, as the name calls it. And we have from the ODCA, and I know you support that, Yannick, introduced the description of DC microgrids as in one of their chapters. There is actually a kind of a maze of substandards in that document. And as a first step, I had mentioned before, the German National Committee has already adopted the system description for microgrids in industry as a standard. So 6364, fundamentals of installation. But
basically amending
you don't have to wait. You don't have to wait for that. Standardization is a very slow moving process. 3 years is considered super fast.
Thank you. So my next question is to Lawrence, related to innovation and industrialization of products. So I've been looking into your very early work from 2017. You have been still PhD student, I guess, at that time. It was towards the universal DC distribution system. And you argued that more generic, interoperable LVDC backbone with integrated protection and arc detection are needed. So as you are working on that nowadays, you basically follow your aspiration. What are the main obstacles to turning research concept like universal DC distribution and smart protection into mass market products that electricians and planners can buy off the shelf?
Yeah, I think the main challenge that we have is that we have a big chicken egg problem, and that is if there's no DC products on the market, nobody builds DC grids, and if nobody builds DC grids, nobody makes products for DC. Yeah? And so I think that's a very important thing to understand. And for example, now recently we had just some discussion with people from the Dutch government again, and they're like, yeah, we have been looking into DC since many years. Why is it not picking up quicker, right? Because it's, and I think the key point is, yeah, we are here in this field and we see a lot of progress, but from the outside, it still looks quite slow. But you really need to create an ecosystem where together we can say, okay, now this makes sense, let's go for it, right? Because in principle, I think a very important factor in general is economies of scale. In electronics. So before you get skill, it's very difficult to compete. Yes, now we have some, so we are now looking for like these business cases or use cases where there's so much benefits that even without skill it works. So for example, this public lighting that I presented today. But for most other normal things, we need economies of scale as well, right? And so somehow we need to solve this chicken egg problem and maybe try to work on these different business cases where they are so good, and then maybe from there we can move on. But obviously we could also just say, hey, we know that we need it, and maybe that could be, for example, this set plan or something like that. Say, hey, okay, government just said, hey, this is a good thing. We are going to do this. In China, they approach it more like that. Then you can also just do it, right? It's just, there's nothing stopping us from, in principle, making DC grids if we would just all say, hey, let's build the next grid that we are building in DC.
I have a follow-up on that. Yes. For me, do you think it is a good idea to piggyback from on supply chain of other industry? To me personally, DC data centers are piggybacking on EV component supply, like cabling, connectors and everything. They can actually reutilize many things. Can be maybe LVDC system people somehow work with battery system people?
Yes, and then maybe I come back to your original question, because I think I think, and that's also the approach that we take. I think what is very important is that we need to realize, in principle, all these things that we realize DC would make sense for everything that we are looking at. Because just if you look at all the things internally, we use almost everywhere DC. And I think that's the very good starting point. That's why I also call that universal DC distribution system. In principle, we need to develop a system that can work for everything on DC. And in that sense, yes, then you can really do that. The danger with this is if you start from something and then say, hey, let's just see what is the next step, and you don't have the big picture in mind, then you're gonna, for example, start making a lot of 48 volt or 24 volt DC system, right? And that works fine for the house, but you cannot connect on 24 volt to your neighbor, right? So I think the very important part is we need to kind of have it in mind. And I think that's, for me, originally, I also started thinking about DC when I was somewhere in Africa in a village without any electricity grid. And I think that's the right way to start thinking, hey, how would we do it then? And then we can come back and see what is the reality and what do we have and how can that help us, what we have now, to get to where we would go eventually. And then maybe you can do some in-between steps. But I think it's very important to not just organically only move a little bit in that step, but have the big picture in mind, because otherwise we can get very easily stuck in something, and then we are not able to really put the next step to make everything DC.
Could be stumble for innovation. Let's see.
Yeah.
Yeah. Thank you. So, and of course, question for Yannick. As you are a president of Current OS, I will ask you as a president of Current OS that from you, but you're also part of a large vendor. So from the point of a large vendor perspective, what ecosystem pieces are still missing, like maybe open protocol, certification schemes, reference architectures, financial models? How in general do you think should either industry or government de-risk DC financially, so to make it more widespread?
So the good news is that we are working on everything that is needed. Bad news is that everything is work in progress. Standards are work in progress. The certification scheme that in the building business is needed is work in progress. The product development is also in progress, etc. There is one thing I think that is not yet started and really missing is the education of professionals. We take care a lot of educating PhDs, but now we also have to educate the engineering consultants in the field, the installers, the people who just put the settings, the electrical inspectors. So all this real field ecosystem, and this is certainly the next objective of foundations like Current OS. The rest is not finished, but we have to start this new.
And we will come back to that.
Yes.
But I will follow up on this in a different way. For example, I know in the Netherlands, many projects like this N470 and others have been de-risked by government by asking for some kind of innovation, and DC was innovation. I think Pulse Building was the same. Could do you see that other countries could consider such schemes when you get support from government to build something, but it should be DC, for example, or it's not realistic to expect?
So country per country, yes, certainly. But that's also part of the work we have done at the DC set plan at the European Commission, is to emphasize not only the research needs and the education needs, but also the regulation needs and everything that at Europe level, but also country level, we could do to have sandboxes and everything to help with these pilots.
Okay. So I would like to conclude this part of the discussion with a flash question to each of you. So is there any business myth around this that you hear repeatedly and would like to publicly debunk right now? Or there are too many?
Well,
I think Harry has 20.
Maybe what you often hear is, oh, the DC arc, and how can I interrupt it? Power electronics takes care of this. It's not an issue, and it has not been an issue with mechanical interruption before either.
I want to say, because what I see as the really big hurdle why things are not moving and what could easily change. And that's why the Netherlands are running quite well, because the politicians, the policy makers has give freedom to move forward in a kind of direction. And that's why now the N470 was the test pilot, but that has resulted in the A16 that makes a tunnel on DC. So and they changed the law for that one. For the tunnel law is changed to make it to DC on a governmental level, because they have learned from enabling things. So in the end of the day, it comes to the policy makers, how you define the rules and how you define the success of DC. And when that, for example, and that's why the interlink converter is so important, because if the policy makers force an interlink converter in every house, because to optimize the power and optimize the impact on the AC system, DC is in there with the speed like USB-C is introduced. In 2016, it doesn't exist. 2017 is mass produced. So that could be the same. But the policymakers have to make decision, and then the market is there. And that's what I want to say. So in the end of the day, it comes to a political level to force the right things. And that's why the set plan is a good plan, but Europe is still too, how to say, market-based and try to avoid policy on technical topics. But if we can fix that one, we have tomorrow on DC World.
Thank you.
Something else we need to debunk is we very quickly, very often have the question, how much costs the DC installation compared to AC? And the problem is people have in mind the AC installation. The answer I provide most of the time is, what does it cost to have no power? Yes. Yeah, so I don't know where I need to restart from, but so the problem is not what the comparison of cost between AC and DC, but the problem is what would it mean for a customer to have no power?
Lawrence, any take on this?
Yeah, I think maybe one more myth. I think it's not really business myth, but I think I want to link to what Hardwick said about ARCs. I think safety is also important one. A lot of people think it's more dangerous to touch DC. But I think it's very important to remember that actually the same risk, and that there's like where basically you have 30 milliampere RCD in AC. In DC, it's 80 milliamperes for the same safety level. So I think it's very often also there's myths there where people think touching DC, for example, also with activating the muscle, so that, for example, you cannot disconnect your hand again if you touch DC. That's not the case. Actually, that is only in AC where your muscles are activated in this way. In DC, you're able to always let go. And but a lot of people, especially electric engineers, they think of that the wrong way around. So that's, I think, and maybe one last one to make it 3. A lot of people also think that DC is less efficient and for transport because of the old days. But in the cable, it's very important to remember also, but a lot of people think that for transmission you need AC. That's not the case. DC is much better for transmission. Back then it was only the voltage level transformation that back then was better in AC. So I would say that's my 3.
Okay, thank you. So we will move towards societal acceptance of DC in general. So maybe I will start from Hartwig again. I will ask you, since you have been involved in certain decision making, and worked so hard on the set plan, as Dmitry said. So if you had the ear of EU policymaker for 5 minutes, what 2 concrete actions would you ask them to take in the next 3 years to unblock LVDC deployment? Your opinion on this?
Well, the 2 things I would ask for regulators to do. One thing I kind of mentioned earlier before is lacking some regulations and standards, give a insurance to people who do it that they are covered in case something should happen. Because actually the largest discussion that one of the examples that I showed, one of the companies there, the largest barrier they had was with the insurance company, because they said, I've never done this, I don't know. And it was, and for that thing, it was covered in a different way, but for that, give them a insurance that should anything happen, because you are a early adopter of a proven new technology that is not widely adopted yet, give them cover. That is number one. And number two would be incentivize installations that initially are, because of economies of scale, more expensive to install.
So basically, you would propose like a two possible financial de-risking schemes for end user and installers.
Yes, exactly.
I see Harry disagrees. Maybe he can go.
Just take the example of electric cars. Electrical cars were, when they introduced, huge expensive, and they don't come down in price. They only come down in price when the policymaker says you shall drive an electric car. And that is the same with the DC part. That's why I try to say is, as long the regulators, as when the EU, and if I was king for one day, I will change one rule, but that means, okay, you will install an interlink converter, and you will make that any prosumer installation is regulated by an ILC through the system. And if that is forced by the policymaker, you don't have a discussion about price, because in the end of the day, it's not the cost what makes the competition. It's the force in the direction, in the overall plan, what is good for the system and what is good for humankind. So it is not, and if you talk about price, it's always good for the person. It's very selfish, because then you get an optimized business case, but it doesn't end up in lower socialized cost. And that's why these products are important. And that's why they need to go to policy. And if they are in a policy, it's there.
I see. So my next question comes to Lawrence, because it's related to protection, because, you know, also many people talk about protection, especially non-professionals on societal level. So basically, you know, safety is a big concern of DC, especially for non-specialists, not so high level people like we have now on the stage. And many people and many electricians don't even know how to use and how to protect DC. So what is your elevator pitch on why modern DC protection and arc detection make LVDC at least as safe as traditional AC? And I know that you are exactly the person who should know the answer to this.
Well, I think first of all the things that I already mentioned about the safety stuff. I think on the topic. So I think in that way we can for sure get the same safety level. I think it's important, especially if you talk about solid state protection. Some people. We have a lot of discussions in standardization about mechanical circuit breakers and things like that. And in AC world, it sounds like a very easy thing to adjust the air in between things, and then you think, oh, that's kind of nice and safe. I think it's quite important to remember that air can actually conduct electricity, and it happens quite violently, but air is not an isolator. Air can actually be ionized, and then you just conduct electricity through air, and it works very well with DC. And I think that's an important thing, that sometimes we have discussions where it's like, yeah, okay, let's add the mechanical switch because then, you know, we are even more safe. I think very often it can actually result in more risk, because mechanical things, they can also fail, and especially with DC. But even with AC as well, mechanical breakers, they also do fail, and in practice, I mean, they almost never operate. That's why maybe you don't notice it often. But if you would go and make short circuit on all the cables in your house, and you do that in the whole city, then you will for sure find a lot of breakers that won't trip properly. And so I think that's the important part, where we need to see, like, if you do DC electronics, those switches, they switch in every single converter. They switch like 100,000 times a second. They can do that very well without a problem. Huh? And I think that's important part, I think, to remember. And then next to that, I think if you're talking about protection, I think, so that's quickly about safety stuff. Otherwise, the other things, I think we can just do the same levels of safety for sure. We can do even better. So for example, public lighting, we can add earth leakage protection that just technically is not possible in AC, because in AC you always charge a cable and you get a lot of leakage current, so you cannot differentiate faults there. So we can improve the safety. And then I think that's maybe not that much about safety, but more about functionality and resilience. And that is with solid state circuit breakers in DC, we can actually make fully selective protection that also works when the power is flowing the other way around. Because traditionally we have power coming from big power plants going down, trickling down the system. That worked all fine. But now that we have all this distributed stuff, maybe cars that can discharge solar, all that kind of stuff, we want to still be able to use those things if there's something wrong in the power system. And for that, we need to make sure that our protection works properly, even if the faults are upstream in the grid. There's also obviously weird situations that can happen in a power system where you, now in the past it didn't matter, because if your cable to your big coal power plant was broken, then anyway there's nothing you can do. But now we have all the distributed stuff, and we expect that we can just use our solar power, as was said earlier today, when it's sunny. Even whatever happens to the grid, we should be still able to use that. So I think that's a very important part in protection as well. And I think with solid state protection DC, we can, well, we have shown that just works very well and very efficiently, and with very little need for like reserve power or things like that.
Thank you. And regarding societal challenges, I think it's also important how we narrate when we talk about DC. So I had a combined question to Yannick and Harry, but I will start from Yannick. Otherwise, Harry will tell everything. So the term DC is still quite technical for most. I mean, we're talking about non-professionals. And what language or narrative actually works with citizens and politicians? Should we talk less about direct current and more about comfort, resilience, lower bills? How should we sell DC to non-technical people?
Well, I think it's a super complex question, and we are all trying to have an answer for this. I'm testing a lot of things. I have tested recently a new narrative. When in your house, you have a fuel heating. This fuel heating doesn't work if you do not have the power grid. And it seemed to be very awkward, but when you have PV on your roof, it doesn't work if the public grid is not on. And this is something that the DC can solve. You can use your power from your roof, even if you have not the grid. And I think we should better start from this to explain what is the resilience. Well, not going to the drop and the reduction of power demand. Well, this will be the next step. But for people that really do not understand anything to anything, that could be a starting point.
I actually agree with this. This is what I also try to narrate myself. But like when people talk about electricity and cost, they talk, okay, 20 cents, 30 cents. I told, how much are you willing to pay if there is no electricity in your city and you can buy it? That's another number. Yeah, Harry, you have a comment, right?
And what is also important, and that is you need a little bit imagination. Because if you go to 100% your target, we want to be CO2 neutral, we want to have all the electricity from renewables. That means technically there is no OPEX anymore in the system. And that's why the whole system will change. And if you think about, that's why if you're a boat owner, that's the happy family A, put it in this way, then you have learned what it means to be independent on your energy and how to survive with your energy. And this behavior will move in the end of the day to everybody. And to make one analogy, also to make it to explain a little bit what is the value for people to communicate, and that is one thing. I always like the example of the phone, because I was grown up when I was calling in, when I was a puber and I was calling my girlfriends in that time. I had more, yes. But my problem was always that my mother was always shouting to me, Harry, hang up, stop calling, it's expensive. Because you pay per minute or per second in that time, and it was expensive. So the phone was seen as a necessary, it was important, but it was not something that you, how to say, embrace. And that phone is changed to a mobile phone. And that mobile phone has kept the trust of the people. If now I touch somebody's phone, I can be killed. And nobody is complaining that I use it in the too long, too much. And that I want to say that is the same thing that will happen to the electricity system. So in the end of the day, if you have renewables, if you have everything, the energy, it's always there because there's so much renewables and you need to adapt that. Then it also comes to the point of trust because you need to bring your installation to your inner circle because that is the area you trust. And that is one thing I think we try to sell because that is in the end of the day. And that was also my question actually to the to the lady. I want to put it in there because if we keep the market model with market pricing, assume that energy always remains in a value that you can have prices. And if you want to achieve in any country, you want to achieve to export energy, what's the value of energy in Europe when every country is exporting? That means you have a negative price, and that means you kill any business case to expand into the electrical market. So if you want to succeed the goal of 100% renewables, you have to get rid of the energy market and you have to introduce capacity tariffs like in telecom. And this capacity tariff, then you pay a fixed fee. And then occasionally you have a lot of energy, sometimes you have less, but that is how you make the system. And if you do that, you'll get a system that people try to optimize, the same as you do on your boat. Sometimes you make a decision not to make a coffee because you want to avoid to start the generator because it is nice sunny weather. So you come to different behavior, and that's one I think that is one of the pitch set.
But you know, I have a maybe counter argument. Right now, what we see an interesting argument in Australia. They're a highly renewable energy country, and they build more and more and big batteries. So what we see this at the end of this year, especially, that big batteries are pushing bottom price up. There is less and less negative or zero prices. Yes. I think that if we will play market model, we will actually narrow down at some point.
But in the end of the day, the energy price will go to zero. And then how to get back, how to pay back your investment. You only can do that in a capex model, not in an opex model anymore.
Actually, I would still have also one quick comment on that because I think that could be one thing, but I think there's also a lot of nice things on energy pricing actually with congestion management, and I think there it's also can be also very useful. I think I offered just one alternative where the price can come from, and that's actually right now it was based on sources because we had marginal cost in the sources, paying for oil, gas, that kind of stuff. And I think we need to eventually move over because now we get wind and solar for zero marginal cost. Eventually, we have to move over to value pricing, basically coming from your consumption. And in the end, driving your car is what determines the value. And then if it's more expensive, eventually we need to have demand response. Or there you say, hey, now it's expensive. Let's set the temperature in our house a bit lower and put on a pullover or something like that. That is where in the end you can still get prices in this kind of system. So, but I think it's a very important thing that in the end it needs to come from the demand side.
Well, one thing to add, because the worst thing that can happen for the energy transition is negative prices. Because if you want to be efficient with your resources and you introduce negative prices, you start to waste energy in a terrible way. That's why in the Netherlands we have, I think, 200 something times a year we have negative prices on the quarter spot, and people turn off their oven in the summer, opening the doors to burn energy to get paid. And this is horrible because at the same time to keep the system active, the big generators need to spin to make sure that the power and the inertia is still provided for wasting of energy of systems. And
but those negative prices, they are because of subsidies. So it's just we need to differentiate that. If you do proper market design, there's very few situations where you could get negative stuff. It would just go to zero and then you get curtailment. I agree, this doesn't make sense. But then you need to talk with the regulators that they shouldn't give subsidy if there's too much. So
So I will wrap up with a flash question. So 30 seconds each. Do you feel more informed? But it's not to you. It's a joke. Actually, it's just to re-energize our auditorium. So everybody are listening? Could you wave your hand? Good, because I see guys are talking and I think you're sleeping. So this is what I'm worried about. So I have one question. So raise your hand if you think the correct answer is yes. Do you feel more informed and confident that you will see more DC in your home in the foreseeable future? your personal home. Okay, 50-50, not bad. Like, chicken. I think we're increasing awareness. Dmitry is still refusing to put PV on his house. I'm pushing him, but let's see. Yeah, but let's see. I will check in 5 years. So I think it's a good moment to move to the very important topic that was raised by Yannick, is educational challenges. And you know that at the point we should recognize that there are serious gaps in curriculums in university relative to LVDC systems design, or even understanding how they properly operate. So I will start from maybe Hartwig. This is a question on a skill gap. If an engineering faculty dean, unfortunately we don't have one here with us today, but maybe to someday other. So if you would, if an engineering faculty dean ask you, what should I change in my curriculum next semester not to fall behind, what would you tell this person?
Good question. I would suggest offer a course called Sustainable Electrification of Our Energy System. And then have subtitles with the topics of resilience, of flexibility, of efficiency. Why do I say that? A professor once told me when he called his electrical engineering program something with sustainability, and he attracted a lot more attention. And that is, we are in a wonderful position. We will electrify our energy system. We're all electrical engineers or electrical people here. What better can happen? But we have to catch the mouse with a cheese and not say, okay, there's a, you know what I mean.
So you think we should first of all
sustainable electrification
not
of the
only
energy.
change, but also narrate it correctly to the students so they actually come and learn.
Yes, because people are motivation driven. And since I'm doing DC and the efficiency and these topics, it's so easy to talk to young people, to family, to nieces and nephews, and so on.
I see. Thank you. So my next question is to you, Lawrence. You know, you are running a company, so you're hiring and probably firing people regularly, as well as I know you take a lot of interns as a students from TU Delft. So my question is other on hands-on learning. So what kind of practical learning environment do you consider essential for young engineers, like DC labs, microgrid demos, digital twins, open test beds, and how can smaller universities or vocational school realistically build them? Because we need not only engineers, but also installers, you know?
Yeah, I think I thought a bit back to the times when I did my PhD in Delft University of Technology, and back then I was one of the first PhD students on DC there, so I worked a lot on really seeing how can we have a good research environment and how can we build all this stuff to put everything together. I think the challenge is that it's not only about the different components, but really how everything can work together. And obviously you can then maybe only in bigger groups like also here in Taltech, where you can really look at all these things together, look at protection, different things. It's very challenging if you only focus on one of the aspects because you're basically missing how you can optimize things and how different things impact each other. But maybe that's not something for everyone, depending on the scale of your budget, maybe. I think now as we move along, there's also obviously way more development going on. There's now products available step by step. So probably it makes a lot of sense to really work together with companies that have things to set something up in common so that you don't need to do everything by yourself. And I think still coming to the question of interns, master students that come from university, I think a very important skill that I think you can never have enough of is actually practical project experience, you know, really doing stuff with your hands and understanding, debugging stuff, understanding if something doesn't work, how do you figure out how you can get it working, right? There's no one right answer, but you need to kind of get a bit of experience on actually doing stuff to be able to work in practice. It doesn't even need to matter what exactly you're doing. And you can build a robot or whatever kind of stuff, but you need to get into that experience. But I think it's also very important just for motivation as well. To do these kind of projects, practical and get that experience so that you can
and to see the result of your work.
Yeah, and then maybe just one remark, maybe still to your previous question about the general question of education. I think since 10 years, I've heard a lot of people always talking about training for installers and things like that. I am always a bit ambivalent on that question because 10 years ago, I was like, yeah, sure, you can train installers, but DC systems are so new that now you'd have to know a lot of stuff. And I think one of the ambitions that I think we have, and I guess all of us in here, is I think our approach is really also to make sure that we make products in the end that have all this complexity built in, so that in the end it's actually super easy to use them. So for example, talking about selectivity in AC, super complex stuff like that, short circuit, how does it work, how's selectivity? Our ambitions is for our solid state breakers, you can just put them together and they are always selective. Right? Then there's not much training needed. You just buy the stuff, connect it, works. And so I think there's also a trade-off where we need to kind of see at what point in time do you need to actually provide this training for whom? But maybe also if you do a good job in the development, actually, then for the end installers in the end, it's actually they just get a Lego set and with the instruction and it's done. And it can be much simpler as well. So I think we can also invest a lot of time in that.
I see there is a counter argument coming.
Yes, I can tell. Sorry, to explain the counter argument, is because electric installer need to be in profession. If it is not a profession, you don't have installers. So if we oversimplify the installation, nobody will install it. So it is important to remember that the profession installer needs to maintain a profession in a proper way. And I've explained that now with the house project, when you have this, I have this local installer, a five-person company. It's very, very small, just to find out how an installer install a DC installation and what they are missing. And actually, I spoke to many people now five people, and interviewed them. And actually, they are crying for respect. They are crying for recognition because there is no way to differentiate themselves because of the small cowboys on the market who do, for example, PV installations. They do it, so their profession is going down in a way. And they have 30, 40 years of experiences. And what was interesting, and that's why the zoning concept comes in, because they saw the zoning really as a classification for their profession again. So of course, when you are in a zone 4 environment, it is very simple. Maybe the guy who do the wallpaper can do the electrical installation. But when it comes to upscale, if it comes down to zone 0, zone 1 or zone 2, or whatever you come, then they see the zoning as a classification for their work, and they are skilled or less skilled, or and they get recognition. And that was the feedback I get. So we have to be careful about communicating to make it too simple, but we have to maintain it as a profession.
Thank you. Yannick, you look like you want to contradict something, no? So anyway, next question is to you whatsoever. Is it working?
I never contradictory. It's a principle.
So, Yannick, you're talking with a lot of companies and you know that all their hurdles and troubles, but you also, being part of a big company, knows that there is expectations from people coming out of universities and coming to work to company. So the question is towards that line. From your perspective, what concrete competency do you want to see in a CV in 2030 for a DC system engineer position? Name 3 skills that you find non-negotiable.
Well, I will start from a little different angle, and Lawrence started here. The only people that understand DC today are the power electronic engineers. And the only people that understand grounding, selectivity, people safety, power availability are AC guys. So what I need is to have electrical engineers to be not only trained or educated to AC, but also educated to DC. And what I need is power electronic guys to understand what is electrical distribution. And guys, power electronic guys, it's not a power supply topic with one power supply and one load. It's electrical distribution start when you have multiple power supply that power multiple loads. And here you need to learn all these kind of things about selectivity, grounding, etc. It's needed. Otherwise, we will not be able to make DC because you will have AC guys that will defend their AC expertise or AC knowledge, and you will be with power electronic lost because you don't have what you need to make a grid.
Thank you. I think it's a good point because we kind of exist in two parallel realities and we need to unite this multiverse, let's say. One more question in this panel before some lightning round to Harry. So what needs to change in the culture of engineering practice and project management so AC trained professionals feel confident to specify and operate DC grids?
Yeah, that comes actually to extend on Yannick's topic. Power system people need to know what power electronics can do, and vice versa. So it is again in and outside the box to understand each other's topologies, because otherwise you can never build systems. And that is also for universities, I think, very important to explain, because when you see the curse of power electronics, you get everything about topologies and you stay on your PCB. And you never leave the PCB outside to something else. And if you do electrical engineering, you connect the PCB, but that's it. And DC is completely overlapping, and that is really needed.
So we need some new kind of integrated programs.
And what I want to add, and that I put in my slide actually, is because technology isn't today, it's more than only technology that is helpful. It becomes part of being, to be, how to say, you don't exist anymore without energy, you don't exist without power electronics, you don't exist without data, whatever, you don't exist. So I think also for universities and for training, it's super important to understand what is the effect of your technology to mankind. And how do you take the responsibility as an engineer. If you design a PCB, what does it mean for the user in the most social way or in the most friendly way? Not only focusing on the datasheet performance, but also focusing on the mankind effects. And this is why it is a system, because systems are there to serve people, and not other way around.
Thank you. So I have only one round of flash questions that I want to pick your mind on. So just try to be a little bit open-minded. So imagine you are in 2035. So 10 years from now. Exactly. And DC is boringly mainstream, but in one domain. Which domain will it be, you think? And how we can make it true? What steps should be taken, in your opinion? You need to select one, Harry. It's for all of you, but I know you need to select one.
It's physical energy communities. Because
sorry, which?
Physical energy communities. Because that is, for me, the highest level of use case. It's the ones with the highest budgets. It's the one with the highest problems. And it brings the highest functionality to manage the energy transition in a proper way.
So DC could be like a tool for natural aggregation of assets.
Yes.
Okay. Thank you. Hartwig, please.
Do you think what I would like to see, or what?
Yeah, what you would like to see.
What I would like to see. I see. Okay. Because I understood your question. What will be there in 20?
You can answer either way.
What I think will be there is data centers will adopt direct current. What I would like to see is widespread adoption of direct current in communities, in residential, and all DC society, if you wish.
Okay. Yeah, I think we are moving there with all the NVIDIA jibber jabber. Lately they haven't built anything, but they talk a lot about it. Yannick, your opinion?
Well, there are two use cases that ramp up very fast at the moment, and data center, you mentioned it. The other one is EV charging. That's the two obvious one. probably public lighting, but it will remain smaller. But the end game is really to have it in our lives, in commercial buildings, in residential things, etc.
I also have to still say something. I would just to differentiate a bit. I would extend a bit. I would say business parks, that kind of stuff, but then really integrating all the new stuff basically. So EV charging, solar, maybe battery, heating, ventilation, heat pumps, that kind of stuff. So all those big power things that we interconnect those on DC, and I would say 2035 should be doable.
Thank you. So before closing the panel, I would like to give an opportunity to attendees to ask several questions, but try not to dig too deep because we are still on the clock. If you have some confusion, please, Arshad.
A person like me, if I share my story, I don't want to dig more, but just to say that by profession, I'm a salesman. I sell Estonian product, and I'm proud that I sold almost about $500,000 worth of equipment out of Estonia to India, to Pakistan, Bangladesh, and Saudi Arabia. When I came to meet Professor Dimitri, I come to learn power electronics, which we call them GPU. I come with the hope that he will teach me how to make the best GPU in Estonia. And when I spent 1 hour with these two gentlemen, they sold me already, which he mentioned the question how we sell DC to public and people who don't understand. So me being in sales, I learned one thing. When you do sale, you need to sell to the right people. And if you find the right people, you don't need to be the pushy salesman. They will buy it anyway. Like myself, when I came and professor explained to me, I said, man, this is very exciting. And after that day, for the past 3 months, I'm promoting this voluntarily. There is no money for it, but I believe in it. So in sales, we say that if you sell something, you need to believe in it. It's like a religion system. You believe that your God is the best, and then you go to preach and become a preacher. So if we think DC is the best, we need to create a belief system like I3DC is doing the job. It's inspired a lot. There is a lot of students being inspired when they dig in what it's doing, and that inspiration bring them to university, not money. That there are people who care for the planet itself, being human, how we survive here, and what is the next plan, and how we need to be accountable for the things that we use on daily basis. So I'm not going to go deep more, but I would say thank you so much for the professor and Andre to collect everybody, because it's been a lot of work has been done here. One of them is me voluntarily. I was supposed to speak there, but unfortunately couldn't. So thank you so much. And picking up the point that we need to educate, especially consultant, we need to bring a space for people like us. Not only me, there will be 100 of them that they want to work with universities or working with these projects and highlight them on international stage. Like I travel on monthly basis, go to Singapore, Dubai, Saudi Arabia for exhibition. And I have no hesitation if a product has potential that they can change, save some money for the stakeholders, they would be happy to adopt them like DC technology. I'm learning now, it's been 3 months, but I would be happy to even take a course here in this university and, learn more and then go out to the industry or the buyer or the user or the distributor and say, we got this technology and this is the future. So the question is that we need to educate, of course, those people like the consultant, or you can call them the people who actually going to take this technology to the market. And his question of selling. So if you sold it to the right people, it will be an easy sell. So thank you so much.
So I don't know how to summarize, but do you think we need a special training for salesmen and consultants, or because technology is not going to sell itself, right?
Well, like you can't sell something that you're not convinced of. I think that's in one sentence what you're saying.
Okay, please.
Yes, I have a question. If we start to start a company, especially in DC side, so which direction we should take here? I mean, especially which subject, or do you have any advice? Or
don't be chicken.
That's the point. That's why I have on my slide failed criminal. And that means if you want to move forward as a startup, as a new company, and if you follow precisely the rules, you cannot move. You will stay inside internally and you burn all your money. So the way you have to do, you have to be very convinced what you're doing. You have to sell it and then make it happen and do it. And then you can grow. So that's why you need to be a little bit a failed criminal, because you have to find the ways there not to walk in the, how to say, if the government say, okay, you have to walk this, you have to do certification, the same as we did in the past. CE marking, of course we have CE marking, we have a CE on it. It's you have a label. So you need sometimes to be a little bit bluffing and to be, don't be chicken, just move.
Yeah, so any more questions? Come to the mic. Mic is not coming to you, it is here.
Thank you. I got a lot of input from you. So my question is, we talk everything about what are the different aspects of DC technologies, but when this is going to happen, so what, as per your experience, what do you think this shifting from AC grid to the DC grid, when this is going to have happened completely across the world, not only in Europe, in the world?
I think I'll go first very quickly. I think a lot of people are always asking, okay, when are we ready? You know, and I think very important thing to realize is so I sometimes have a discussion and they're like, yeah, are the things already in the market? And then it's no, not yet on the market. And then okay, I'll come back in 5 years. Nothing will happen in 5 years if the customers are not involved. You know, you need to have these projects that really push this development and say, I mean, we are a small company, we are constrained in certain things, but also the big companies, they only get approval to develop stuff if they can show, if the guys that want to do it, if they can show that there's a market demand as well, right? So I think it's very important to realize that we really have this chicken egg problem, and so it doesn't happen by itself, but it can just happen any moment, right? If you just come together and say, hey, big construction projects, stuff like that, enough scale, we can develop all the stuff that's needed. We can immediately do it, and then in development cycles in 2 years, we can have everything in mass production in principle. Huh? The question is just how do we get the critical mass together to make it happen, and that could happen now or in 2 years or in 10 years. It just depends on us how we can bring the right set of people together to make it happen.
I started my career in the 1990s, 80s, and in the 80s, I had colleagues working on contactors, and a few crazy guys that started to put variable speed drive and power electronics to drive motors. And at the time, they need to prove that this very big, very costly, and very eating device was more efficient than the simple, stupid contactor they were using. They had no standard. The customer were not learning, and look what happened less than 20 years after, less than 15 years after. It was a mainstream, and nobody today would consider that variable speed drive is less efficient than a contactor. So I think DC is the same, and we are, I would say, more or less in the middle of the journey. So I think that between 5 and 10 years, it will become mainstream for the same reason. We are working on standard. We are working on educating. So still a lot of things to be done, but I think nothing we cannot overcome.
Yeah, but team is growing, right?
Absolutely. And yes, I was thinking about this at the time also. So crazy guys in the 80s making the variable speed drive were just one expansion of the team. You know, all the wild duck they had in the team were working on this. And after some years, it became a specific team, and then a dedicated division, or now it's a pure business unit. And I think DC will have the same way in all our companies. So today we are, I would say, in the middle of the process, the journey.
Baby steps, like with everything, I guess.
Yes, like, is this a closing statement or?
Yeah, I guess so. I think we need to wrap up anyway. So.
Yeah. Will there still be AC in 50 years? Yes. Will most of the stuff be DC? Yes.
And it's simple. if you choose, you have to understand what you don't have if you choose the other. And that's why I think in the end of the day, and it's very seldom you hear that from me, but I like DC, but sometimes AC makes also sense. And
that's big from you, Harry.
It's very brief, but I have because one of the professors I had discussion, Lou van der Sluis, he always says, Harry, if you choose something, you don't have the other. That you have to understand. So you always choose of the positive arguments, but you never choose what you have lost. And that's why sometimes it's important to do that. And I think that's why it will be in a hybrid world. And if it's a hybrid world, then you have the best of both. And that's why the comparison, apple and passion fruit, is so important.
So I would like to thank our panelists. Applause, please.